Imagine looking up at the night sky and feeling that deep, familiar sense of wonder, the same awe that has captivated human beings for thousands of years. We see the stars, the planets, the silent dance of galaxies, and it all seems so permanent, so beautifully ordered. But what if I told you that everything you're seeing is not unfolding on some fixed, unchanging stage? What if the universe is more like a living, breathing fabric, a cosmic tapestry that bends, stretches, and ripples under forces we can't see, but whose effects shape every single thing that moves, from the smallest atom to the largest cluster of galaxies? This is the world of spacetime, not an empty void, but a dynamic, almost fluid entity that has been mystifying and inspiring some of the greatest scientific minds for more than a century. It all began with a revolution in thought, Albert Einstein's stunning realization that gravity isn't some mysterious force acting across vast distances, but rather the curvature of spacetime itself. Mass and energy don't just exist within space and time. They mold it, they shape it, they bring it to life. And in this video, we're going to pull back the curtain on the invisible engines behind this extraordinary cosmic choreography. We'll explore how everything from the warmth of sunlight to the crushing density of a black hole, from the restless buzz of the quantum vacuum to the baffling push of dark energy, all of these act as sculptors of reality, guiding the motion of the cosmos in ways that continue to surprise and humble us. This isn't just a story about abstract ideas or far-off wonders. It's a journey to the heart of how the universe actually works, a chance to see beyond the surface and into the hidden mechanics that govern existence itself. By the time we're done, you won't just understand what spacetime is. You'll feel what it means to be part of something so much larger, so much more dynamic and mysterious than everyday life suggests. So come with me. Let's venture together into the depths of general relativity, peer into the quantum foam, and confront the enigma of dark energy. Prepare to see the cosmos not as a static picture, but as a living, evolving masterpiece, a symphony written in the language of curvature, motion, and light. Your perception of reality is about to change forever. Think of the universe not as a stage, but as the lead actor in its own grand performance. This is the profound shift in thinking that Albert Einstein gifted to the world. Before him, space was imagined as a static, empty container, a vast, inert nothingness where objects moved under the influence of mysterious, invisible forces like gravity. But Einstein saw something far more elegant and interconnected. He realized that space and time are not separate entities. They are woven together into a single, dynamic fabric called spacetime. This fabric isn't just a backdrop. It's a responsive, pliable medium that reacts to the presence of mass and energy. A massive object like our Sun doesn't reach out across empty space to pull on the Earth. Instead, it creates a deep, curving dent in the spacetime around it. And our planet simply follows the natural contours of that curve, like a marble rolling around the inside of a bowl. This is the essence of gravity, not a force, but geometry. To truly visualize this, picture a taut trampoline. If you place a small, lightweight ball on it, it barely makes a dent. The surface remains mostly flat, but now place a heavy bowling ball in the center. The fabric stretches and warps dramatically, creating a steep, curved valley. If you then roll that same small ball onto the trampoline, it won't travel in a straight line. It will spiral inward, orbiting the central depression before eventually making contact. This is a beautifully simple analogy for how our solar system works. The Sun is that bowling ball, creating a gravitational well in the fabric of spacetime, and the planets are those smaller balls, forever circling in the curved paths dictated by the shape of that cosmic terrain. Einstein himself captured this symbiotic relationship with a now famous phrase: "Matter tells spacetime how to curve, and spacetime tells matter how to move." It's a cosmic dialogue, a continuous feedback loop where the actors shape the stage and the stage, in turn, directs the actors. The mathematics that describe this conversation are his field equations, a set of incredibly complex formulas that precisely relate the curvature of spacetime to the energy and momentum within it. While the full equations are the domain of advanced physics, their message is powerfully intuitive. The universe is a flexible, dynamic entity where matter and the very fabric of reality are in a constant, intimate dance. Now, just imagine if you could perceive this directly. What if you had goggles that allowed you to see the invisible topography of the room you're in right now? You might see gentle dimples beneath every object, your chair, your coffee cup, even yourself. You'd see the subtle warping caused by the Earth's mass beneath your feet. Looking up at the sky, you wouldn't see blank, black space. You'd see a breathtaking landscape of curves and wells, with planets tracing graceful grooves around our star, and the entire solar system falling through a grand galactic curvature created by the Milky Way. Your entire perception of motion, of falling, of orbit would be transformed. You wouldn't feel pulled down by gravity. You'd feel yourself simply navigating the slope of the universe. This revolutionary view of spacetime as a dynamic fabric is the foundation for everything that follows. It's the first and most crucial step in unraveling the invisible engines that drive the cosmos. So if spacetime is this incredible, malleable fabric, what is it that actually does the bending? What are the hands that shape this cosmic clay? The most direct and powerful sculptor, the one we're all intimately familiar with, is mass. Every single thing that has mass, from the phone in your hand to the planet beneath your feet, creates a dent in the fabric of spacetime. It's a universal rule: where there is matter, there is curvature. This is the heart of gravity as we understand it through Einstein's eyes. It's not a mysterious force reaching out across the void. It is the direct consequence of an object's presence warping the very stage upon which the universe performs. Take our own moon, for instance. We often say Earth's gravity holds the moon in orbit, but that's a simplified, almost outdated way of seeing it. A more precise picture is that Earth's substantial mass creates a profound, planet-sized well in the spacetime around us. The moon, in its journey, is simply following the gentlest, most natural path it can along the curved contour of that well. It's not being pulled, it's rolling, like a marble circling the drain of a basin. The renowned physicist Kip Thorne beautifully reframed this, explaining that gravity is not a force in the traditional sense, but the geometry of spacetime itself. The paths of planets and stars are not dictated by invisible strings, but by the hills and valleys of this invisible landscape. And if mass creates a dent, then an overwhelming concentration of mass creates the ultimate cosmic abyss, a black hole. Imagine taking the mass of a giant star, millions of times the mass of our Sun, and compressing it down into an infinitely tiny point, a singularity. The spacetime around this point doesn't just curve, it collapses in on itself, forming a gravitational well so infinitely deep that it becomes a one-way street. The curvature at the edge of this pit, the event horizon, is so extreme that the path of anything that crosses it, even light itself, bends completely inward, never to return. It is the bottomless pit in the fabric of reality, a place where the rules of physics as we know them are stretched to their absolute limit. This profound curvature doesn't just affect the paths of objects, it warps time itself, a phenomenon known as gravitational time dilation. Picture two identical clocks, both perfectly synchronized. Now, place one clock here on Earth and the other far out in deep space, where spacetime is much flatter. You would observe that the clock in the stronger gravitational field here on Earth actually ticks slower. The difference is tiny for us, but near a black hole, this effect becomes staggering. Try to imagine, for a moment, approaching the event horizon of a black hole. From your perspective, your clock would seem to tick normally. But to an observer watching you from a safe distance, your movements would appear to slow down, slower and slower, until you seem to freeze completely at the very edge, your image stretched and reddened before fading from view. Time itself grinds to a halt at the precipice. This isn't science fiction, it's a direct prediction of general relativity, confirmed by incredibly precise experiments right here on Earth. It shows us that mass doesn't just shape where things can go. It fundamentally shapes the very flow of time, weaving the threads of space and time into an inseparable, dynamic whole. But while mass is the most obvious sculptor of spacetime, it is far from the only one. Einstein's genius was to reveal a deeper, more democratic truth. It isn't just mass that tells spacetime how to curve, but all forms of energy. According to his famous equation, E=mc², mass and energy are two sides of the same coin. They are fundamentally interchangeable. This means that a beam of pure light, which has energy but no mass at all, still creates a tiny, almost imperceptible dent in the cosmic fabric. The heat from your morning coffee, the kinetic energy of a speeding car, even the chemical energy stored in a battery, all of it contributes to the grand, invisible topography of the universe. Their individual effects are extraordinarily small, but they are undeniably there, woven into the very laws that govern reality. This idea was perfectly captured by the great physicist Richard Feynman when he said, "Mass is just a form of energy, they are interchangeable." This isn't just a poetic statement, it's a foundational pillar of modern physics. It means that if you take an object and simply speed it up, you are increasing its energy, and therefore, ever so slightly, increasing its gravitational pull. A fast-moving baseball, for instance, would have a minutely stronger influence on spacetime than the same baseball sitting perfectly still on a table. We don't notice this in our daily lives because the effect is vanishingly small, but on cosmic scales or in extreme environments, this principle becomes profoundly important. We can actually create these extreme environments ourselves, in massive laboratories like the Large Hadron Collider. Inside that 27-kilometer ring, we accelerate protons to within a fraction of the speed of light, concentrating a tremendous amount of energy into a space far smaller than a single atom. In that fleeting moment of collision, for a split second, we are creating a microscopic, intensely curved region of spacetime, a tiny gravitational firestorm born not from mass, but from pure, raw energy. It's a stunning demonstration of Einstein's theory in action, showing us that gravity is a consequence of all energy, not just the kind that has weight. To push this idea to its theoretical limit, consider a purely imaginative experiment. What if you could build a box with perfectly reflective mirrors on the inside, and you filled that box with nothing but light, with photons bouncing back and forth? Even though those photons are massless, they carry energy and momentum. According to general relativity, if you could concentrate enough light into that box, that confined energy would actually begin to generate its own gravitational field. An outside observer would be attracted to the box, not because it has mass, but because it contains an immense density of energy. It's a powerful thought that challenges our basic intuition and shows us that the universe operates on a logic far richer and more surprising than we might assume. This opens up a world of fascinating possibilities for the far future. If all energy curves spacetime, could we one day learn to manipulate gravity not with massive objects, but with concentrated energy fields? Could we engineer spacetime itself by controlling these energetic influences? While this remains firmly in the realm of speculative science, it forces us to expand our view of what's possible. It teaches us that the engines of the cosmos are more diverse and subtle than we first imagined, and that the most profound influences on the universe often come from the most unexpected places. So we've seen how mass creates gravity's dominant curve, and how pure energy, even from light, adds its own subtle warp to spacetime. But the story doesn't end there. Einstein's equations reveal an even more intricate detail. The full gravitational influence of an object isn't just about its mass or its energy. It's also about its internal state. This brings us to a truly hidden engine, one operating in the heart of every star and planet: stress and pressure. These are the invisible forces pushing outward against the relentless crush of gravity, and according to the laws of general relativity, they too contribute to the curvature of spacetime. It's a concept that feels almost counterintuitive. We usually think of pressure as something that pushes back, that resists. But in the cosmic fabric, that very act of pushing outward actually adds to the overall gravitational pull. To understand this, let's look at our own sun. We know its enormous mass creates the gravitational well that keeps our entire solar system gracefully orbiting. But the sun isn't just a static ball of gas. Deep in its core, the incredible pressure and temperature from nuclear fusion are generating a tremendous outward force. This pressure is what keeps the star from collapsing under its own immense weight. It's a constant, titanic struggle between gravity pulling inward and pressure pushing outward. Now, here's the extraordinary part. That internal pressure doesn't just fight gravity. It also, according to Einstein's math, enhances it. The stress and pressure within the sun actually make its gravitational field slightly stronger than it would be if the sun were simply a cold, inactive ball of mass. It's as if the star's fiery heart is not only maintaining its structure, but also deepening the very gravitational well it sits in. A simple analogy can help make sense of this. Imagine that taut trampoline again. Placing a heavy bowling ball in the center creates a deep dent, representing the curvature from mass. Now, imagine that bowling ball is actually a powerful, inflatable sphere. As you pump more air into it, its internal pressure increases and it pushes outward against the trampoline fabric with even greater force. This doesn't lift the ball up. Instead, it stretches the fabric further, making the central depression even deeper and steeper. The internal pressure of the object has actively contributed to the warping of the surface. In a very similar way, the intense pressure inside a star adds an extra layer of curvature to the spacetime around it. This principle becomes absolutely critical when we look at the most extreme objects in the universe, like neutron stars. These are the collapsed cores of giant stars, and they are laboratories of unimaginable physics. A neutron star packs more than the mass of our entire sun into a sphere only about the size of a city. The density is so absurdly high that a single sugar cube-sized piece of this material would weigh as much as a mountain. The pressure at the center of such an object is beyond human comprehension. It's enough to crush atoms themselves, squeezing protons and electrons together to form a superfluid sea of neutrons. In this environment, the contribution of pressure to spacetime curvature is no longer a tiny, subtle effect. It becomes a dominant player. The internal pressure of a neutron star is so immense that it significantly alters the local geometry of spacetime around it, affecting how it spins, how it pulls on companion stars, and even how it emits gravitational waves. Astrophysicists studying these cosmic zombies have to account for pressure's gravitational role to accurately model their behavior. And while the pressures we encounter in our daily lives, the air pressure in our tires, the water pressure at the bottom of a swimming pool are far too weak to produce any measurable spacetime curvature, they are, in principle, part of the same universal mechanics. The gentle push of the atmosphere on your skin, the structural integrity of the ground beneath your feet. All of these are minuscule manifestations of the same forces that, when scaled up to stellar proportions, become fundamental architects of cosmic structure. This reveals a universe where nothing is passive, where even the internal struggles of an object contribute to the grand, geometric tapestry of reality, setting the stage for us to consider engines that are even more abstract and mysterious. Now, if mass, energy, and even internal pressure can all shape the spacetime around them, What happens in the apparent emptiness between galaxies? What is the nature of pure, unadulterated space itself? This question leads us to one of the most fascinating twists in the history of science, and to an engine so subtle that even its own creator initially dismissed it: the cosmological constant. This is the story of how Albert Einstein, in a way, was both profoundly wrong and spectacularly right, and how the greatest vacuum of space is actually teeming with a mysterious, repulsive energy that is actively stretching the very fabric of the cosmos. In 1917, Einstein was applying his magnificent new theory of general relativity to the entire universe. Like most scientists of his day, he believed the cosmos was static, eternal, and unchanging on the largest scales. But his equations told a different story. They predicted that a universe filled with matter should either be expanding or contracting. It could not remain still. Unwilling to abandon the idea of a steady-state cosmos, Einstein did something uncharacteristic. He tweaked his own pristine equations. He introduced a new term represented by the Greek letter lambda, which he called the cosmological constant. This was a kind of anti-gravity force, a uniform energy inherent to the vacuum of space itself that would perfectly counteract the gravitational pull of matter, propping the universe up into a state of perfect, balanced stillness. He had, in essence, engineered a solution to keep the universe static. But just over a decade later, the astronomer Edwin Hubble made a monumental discovery. By observing distant galaxies, he found that the universe was not static at all. It was expanding, with galaxies all rushing away from each other as if from a primordial explosion. Einstein realized his intervention had been completely unnecessary. The equations, in their original, unadulterated form, had been trying to tell him the truth all along. He famously called the introduction of the cosmological constant his greatest blunder, and the concept was largely shelved by physicists for decades, seen as a curious historical footnote, a moment of hesitation from a genius who otherwise charged forward with unwavering confidence. The story, however, was far from over. Imagine this constant not as a mistake, but as a hidden spring woven into the very foundation of reality, a spring that, when compressed, wants to push back. For most of the universe's history, the outward push of the initial Big Bang and the inward pull of gravity were the dominant forces. But what if, as the universe expands and matter thins out, the gentle, constant pressure of that hidden spring finally begins to dominate? This is precisely what two independent teams of astronomers discovered in the late 1990s. They were measuring the distances to extremely faraway supernovae, using them as cosmic mile markers to gauge how the expansion rate of the universe has changed over billions of years. Everyone expected to find that the expansion was slowing down due to the collective gravitational brake of all the matter in the cosmos. To their complete astonishment, they found the opposite. The expansion was not slowing, it was speeding up. Something was acting against gravity, pushing galaxies apart with ever-increasing force. The universe's acceleration demanded an explanation, and the most straightforward one was the resurrection of Einstein's cosmological constant. It wasn't a blunder, it was a prediction. This lambda term represented a uniform energy density permeating the vacuum of space, a dark energy that makes up about 70% of the entire energy content of the universe, and whose repulsive gravity is now stretching the cosmic fabric at an accelerating pace. This discovery forces us to confront some of the most profound questions about our ultimate destiny. If this accelerated expansion continues unchecked, what does it mean for the far, far future? We might be living in a universe destined for a big freeze, where galaxies rush apart so rapidly that the sky beyond our local group grows dark, and the universe becomes an increasingly cold, isolated, and empty place. But is this acceleration truly constant, as Einstein's original term suggested? Or could it evolve over time, perhaps leading to an even more dramatic fate. The reintroduction of the cosmological constant didn't just solve one mystery. It opened a portal to a much deeper enigma, forcing us to ask what empty space truly is if it isn't empty at all, but alive with a mysterious energy that holds the keys to the fate of everything. So if the cosmological constant suggests that empty space is brimming with a mysterious, repulsive energy, what could possibly be the source of that energy? To find the answer, we have to venture away from the grand, curved landscapes of general relativity and plunge into the bizarre, frenetic world of the very small, the quantum realm. Here, the very concept of nothing ceases to exist. The vacuum of space is not a still, silent void. According to quantum mechanics, it is a seething, turbulent ocean of activity, a place where the laws of physics allow for a strange and permanent state of chaos. At this microscopic scale, the calm fabric of spacetime gives way to a boiling, frothing foam, where particles and energy flicker in and out of existence in a relentless, unpredictable dance. This phenomenon is known as quantum fluctuation, and it is one of the most astonishing predictions of modern physics. The famous Heisenberg uncertainty principle tells us that we can never perfectly know both the energy of a system and the exact time that energy exists. This isn't a limitation of our measuring tools. It's a fundamental property of the universe itself. This uncertainty opens a door, a tiny loophole in the law of energy conservation that allows for something incredible to happen. For fleeting moments, pairs of virtual particles, one matter and one antimatter, can spontaneously burst into existence, borrowing energy from the vacuum before annihilating each other and paying that energy back almost instantly. The universe is constantly running a cosmic tab, and these particles are the briefest of transactions. The best way to visualize this is to think of a pot of water just before it boils. You see tiny bubbles forming and popping at a furious pace across the entire surface. Each bubble is a temporary event, a tiny pocket of activity that appears from nowhere and vanishes just as quickly. Now imagine that on an unimaginably smaller scale, the very fabric of reality is behaving exactly like that water. Every single point in space is a potential site for one of these bubbling events. Each virtual particle pair is like one of those bubbles, a momentary flicker of existence in an otherwise seemingly empty pot. This isn't just a theoretical idea. We have experimental proof that this quantum foam is real. The Casimir effect, for instance, demonstrates that if you place two incredibly smooth metal plates extremely close together in a vacuum, the countless quantum fluctuations outside the plates will exert more pressure than the more limited number of fluctuations that can occur between them, actually pushing the plates together. The invisible activity of the vacuum has a tangible, measurable force. This chaotic quantum sea doesn't just exist separately from the curved spacetime of general relativity. It interacts with it in profound ways. All that flickering energy, according to Einstein's own rules, should curve spacetime. Every virtual particle pair, in its brief life, has mass and energy, and therefore it creates a tiny, temporary dent in the cosmic fabric. On the human scale, the combined effect of these trillions upon trillions of microscopic curvatures averages out to something we don't notice. But on the Planck scale, the smallest possible scale of distance, spacetime itself is thought to be a churning, chaotic foam, its very geometry fluctuating wildly because of this relentless quantum activity. This interaction becomes spectacularly important near the most extreme objects in the universe, black holes. This is where Stephen Hawking made his revolutionary contribution. He realized that these quantum fluctuations don't just happen in empty space. They happen everywhere, including right at the edge of a black hole's event horizon. Imagine a virtual particle pair popping into existence so close to the edge that one particle falls across the horizon, into the black hole's clutches, while the other manages to escape outward into space. From the perspective of the outside universe, The black hole has just emitted a particle. The escaped particle carries away real energy, and to conserve energy overall, the particle that fell in must have had negative energy, which effectively reduces the black hole's mass. Over astronomical timescales, this process, known as Hawking radiation, causes black holes to slowly evaporate. The mighty black hole, the ultimate manifestation of gravity's power, is ultimately vulnerable to the faintest whisper from the quantum vacuum. This incredible discovery also highlights the greatest unresolved conflict in all of physics, the problem of quantum gravity. General relativity gives us a beautiful, classical description of spacetime as a smooth, continuous fabric. Quantum mechanics gives us a description of particles and fields that is inherently probabilistic and chaotic. When we try to combine them to describe the center of a black hole or the first moments of the Big Bang, where both gravity and quantum effects are unimaginably strong, the math completely breaks down. The equations of quantum field theory, when applied to the energy of the vacuum, predict a curvature of spacetime so enormous that the universe should have ripped itself apart instantly after the Big Bang. Yet, our actual universe is here, and the observed effect of vacuum energy is over 120 orders of magnitude smaller. This is not just a small error. It is the largest discrepancy between theory and observation in the entire history of science. It tells us in no uncertain terms that we are missing a fundamental piece of the puzzle, a deeper theory that can harmonize the smooth geometry of gravity with the chaotic frenzy of the quantum world. This grand challenge naturally leads to a tantalizing question. If the vacuum is truly this bubbling cauldron of energy, could we ever learn to tap into it? Could we somehow harness these quantum fluctuations as a source of power? The idea has certainly fueled science fiction for decades, promising limitless energy from the very emptiness of space. The reality, unfortunately, is far more daunting. By its very nature, this energy is virtual, it's borrowed, and must be paid back almost instantly. To extract usable, sustained energy from the vacuum would require a way to stabilize these fleeting fluctuations, to prevent the particles from annihilating, which would violate the very quantum principles that allow them to exist in the first place. While there are fascinating theoretical ideas about manipulating the vacuum state, the consensus is that harvesting this so-called zero-point energy is likely impossible. But the fact that we can even pose the question shows how far our understanding has come. We now look at the void and see not emptiness, but potential, a hidden, turbulent engine whose full role in shaping the cosmos remains one of the deepest mysteries we have ever encountered. But for all the power of mass, energy, pressure, and the quantum vacuum to shape the cosmic stage, there remains a colossal piece of the puzzle that we cannot see, touch, or directly observe. A ghostly presence whose influence is felt across the vastness of entire galaxies. This is the enigma of dark matter. Imagine looking at a gigantic, spinning pinwheel galaxy, a beautiful island of billions of stars. You can see all of its luminous parts, the bright central bulge, the spiral arms traced by blue giant stars and glowing pink nebulae. According to the laws of gravity and motion that we understand so well, the stars on the outer edges of this galaxy should be moving much more slowly than those near the center. Just as Pluto orbits our Sun at a far more sedate pace than Mercury, a star on the galactic fringe should be crawling along its orbital path, held by the weakening gravitational grip of the distant core. Yet, when astronomers like Vera Rubin began to measure the actual orbital speeds of these stars in the 1970s, they found something that defied all expectations. The stars far out in the galaxy's suburbs were not moving slowly at all. They were whipping around at nearly the same high speed as the stars close to the bright center. It was as if the entire galaxy was spinning like a rigid solid, a single piece of vinyl on a turntable, rather than a vast system where gravity should fade with distance. The only plausible explanation was that there had to be far more matter in the galaxy than what was glowing in their telescopes. This matter wasn't concentrated in the center. It had to be spread throughout the galaxy and far beyond the visible edge, forming a massive, invisible spherical halo whose gravity was the true conductor of this stellar symphony. The visible galaxy, the part we can photograph and admire, was merely the brightest core embedded within a much larger, unseen structure. The pioneering astronomer Vera Rubin, whose meticulous work provided the most compelling evidence for this phenomenon, put it succinctly: "What you see in a spiral galaxy is not what you get." Her observations forced the scientific community to confront a startling reality. The stuff that makes up you, me, our planet, and every star we can see, the atoms and molecules of ordinary matter, accounts for less than 20% of the total matter in the universe. The overwhelming majority, the other 80% or more, is this mysterious dark matter. It does not emit, absorb, or reflect any light. It is completely invisible across the entire electromagnetic spectrum. Its presence is known only through its one undeniable interaction: gravity. It creates the deep, extensive wells in spacetime that entire galaxies form within. A powerful way to picture this is to think of a city at night, seen from a high-flying airplane. You can see the streetlights, the headlights of cars, the illuminated windows of buildings. That's the visible matter, the stars and gas of a galaxy. But what gives the city its shape and holds it together? It's the unseen infrastructure: the roadways, the foundations, the steel girders, the electrical grid. You don't see these things directly from the air, but without that invisible scaffold, the city would have no structure and would simply collapse into chaos. Dark matter is the cosmic version of that infrastructure. It is the invisible framework upon which the visible universe is built, the hidden architecture that dictates how galaxies form, how they spin, and even how they collide with one another. The hunt to identify what dark matter actually is constitutes one of the greatest detective stories in modern science. We know it has mass and feels gravity, but it seems to interact with ordinary matter through none of the other fundamental forces, or does so weakly that we haven't been able to catch it in the act. The leading candidates are hypothetical particles that were born in the early universe. One prominent idea is that dark matter is made of WIMP, or weakly interacting massive particles. These would be heavy particles that don't interact via the electromagnetic force, making them dark, but might occasionally bump into the nucleus of an atom. Deep underground, in abandoned mines and tunnels shielded from cosmic rays, incredibly sensitive experiments are waiting, hoping to feel the faintest tap from a WIMP passing through the Earth. Another compelling candidate is the action, an extremely lightweight particle predicted by theories that solve certain problems in particle physics. These would be far more abundant but even harder to detect, behaving like a pervasive, ghostly fog flowing through everything. This ongoing search forces us to ask a deeply philosophical question: what is the universe truly made of? We have built our understanding of reality on the foundation of atoms, but we are now confronted with the humbling fact that most of the material cosmos is built from something entirely different, a substance whose nature is completely unknown to us. Is dark matter a single type of particle, or a whole family of them? Could it be that our understanding of gravity itself needs a fundamental revision on galactic scales, a possibility explored in theories like modified Newtonian dynamics? Or does the answer lie in something even more exotic, waiting to be discovered in the data from a deep underground lab or a particle accelerator? The mystery of dark matter is a profound reminder that the invisible engines driving the cosmos are not just subtle influences. They can be the dominant architects of reality, hiding in plain sight, their presence written not in light, but in the silent, relentless motion of the stars. So if dark matter is the invisible glue holding galaxies together through its gravitational pull, what mysterious force could possibly be acting in direct opposition, pushing the entire universe apart on the grandest of scales. This brings us to the most dominant and most perplexing component of our cosmos: dark energy. Think of it as the ultimate counterweight to gravity, a pervasive, repulsive force that is not pulling matter together, but is instead stretching the very fabric of spacetime itself, causing the expansion of the universe to accelerate at an ever-increasing rate. While dark matter works to build cosmic structure, dark energy seems intent on tearing it all apart on the largest scales, acting as the dominant engine driving the ultimate fate of everything we see. The best way to wrap your mind around this is to think of the universe not as galaxies flying apart through space, but as the space between galaxies actively growing. A wonderful metaphor is a loaf of raisin bread baking in the oven. Imagine the dough represents the fabric of space-time, and the raisins are galaxies. As the bread bakes and rises, the dough itself expands. From the perspective of any single raisin, all the other raisins are moving away. The raisins aren't actively traveling through the dough. They are being carried apart by the expansion of the dough itself. Now, imagine that the yeast in the bread gets more potent over time, causing the dough to rise faster and faster. That accelerating expansion is precisely what dark energy is doing to our universe. Every single unit of space is continuously stretching, and that stretch is intensifying, pushing galaxies apart at a rate that will only increase with time. This isn't just a theoretical idea. It's one of the most robust findings in modern cosmology, confirmed by painstaking observations. The original discovery in the late 1990s, which earned the Nobel Prize in Physics in 2011, relied on measuring distant supernova exploding stars that serve as standard candles, allowing astronomers to gauge cosmic distances with incredible precision. The Hubble Space Telescope was instrumental in this work, and its successor, the James Webb Space Telescope, is now refining these measurements to an even greater degree, peering back to see if the strength of dark energy has changed over the deep history of the cosmos. The data consistently tells the same startling story. About 5 billion years ago, the expansion of the universe transitioned from slowing down due to the gravitational tug of all matter to speeding up as the repulsive effect of dark energy began to dominate. But what is it? The leading hypothesis, as we touched on with the cosmological constant, is that dark energy is an intrinsic property of the vacuum of space, a fixed energy density that exerts a negative pressure. But another compelling theory suggests it might be something dynamic and evolving, a concept physicists call quintessence. Named after the classical fifth element believed to fill the universe beyond Earth, quintessence imagines dark energy not as a constant, but as a mysterious field that could vary in strength over time and space. Perhaps it weakened in the early universe, allowing gravity to form galaxies, and is now strengthening, driving the acceleration we see today. This possibility opens up a range of dramatic futures, from an eventual Big Rip, where the fabric of spacetime is torn apart at every scale, to a scenario where the acceleration might one day reverse. Ponder that for a moment. Why does dark energy exist at all? Why does the vacuum of space have this bizarre, repulsive property? And why does it have the specific strength that it does? The value of the dark energy density is one of the most perplexing numbers in all of physics. If it were significantly larger, the universe would have expanded so rapidly that stars, planets, and life could never have formed. If it were much smaller, it wouldn't have been noticeable, and the universe might have recollapsed long ago. Its value seems almost perfectly tuned to allow for a universe that can first form galaxies and then accelerate them into darkness. This profound fine-tuning is a mystery that leads some to consider the anthropic principle, the idea that we observe these specific constants because they are necessary for our existence, or to speculate about a vast multiverse where every possible value plays out in different realities. Contemplating the long-term future under the reign of dark energy is a truly humbling exercise. If the acceleration continues unabated, tens of billions of years from now, the universe will become a very lonely and dark place. Galaxies outside our local group will be pushed so far away that their light will no longer be able to reach us, redshifting into complete invisibility. The cosmos will appear to any future observers as a single, isolated island galaxy adrift in an infinite, expanding blackness. The evidence for a Big Bang will be erased from the sky, and the universe will grow cold, silent, and empty. This potential fate, known as the heat death or Big Freeze, is the ultimate expression of dark energy's power, an invisible engine that doesn't just move objects within the universe, but actively engineers the universe's final state, guiding it toward a profound and eternal stillness. For centuries, astronomy has been a science of silence, a discipline of watching the cosmos but never truly hearing it. We have built our understanding of the universe by collecting light photons of every wavelength, painting a magnificent but incomplete picture. But what if we could finally listen? What if the universe had a soundtrack, a symphony of vibrations played on the very fabric of reality itself? This is the profound revolution ushered in by the discovery of gravitational waves. These are not waves of light or sound. They are literal ripples in the fabric of spacetime, distortions that travel outward at the speed of light from the most violent and energetic events in the cosmos. They are the direct, physical evidence that spacetime is not a static stage, but a dynamic, fluid medium that can be stretched and squeezed, much like the skin of a drum that has been struck. The best way to picture this is to go back to our trampoline analogy. Imagine dropping a heavy ball onto its taut surface. You see the impact create a deep dent, representing the curvature from mass. But in the moments after that impact, you also see a series of ripples radiate outward from the center, traveling all the way to the edges. Those ripples are the trampoline's version of gravitational waves. Now, scale that up to a cosmic cataclysm. When two immensely dense objects, like black holes or neutron stars, spiral inward and finally collide, they don't just create a new, stationary dent in spacetime. Their incredible acceleration, their violent orbital dance and final merger, sends powerful shockwaves racing outward through the cosmic fabric. These waves compress and stretch space itself in a perpendicular pattern as they pass by, literally changing the distance between objects, albeit by an almost infinitesimally tiny amount. For decades, these waves were a beautiful prediction of Einstein's theory, but they were thought to be so faint that detecting them would be impossible. The distortion they cause is smaller than the width of a proton over a distance of 4 kilometers. It seemed like a hopeless task. That is, until the Laser Interferometer Gravitational Wave Observatory, or LIGO, achieved the impossible. On September 14, 2015, after decades of development and refinement, LIGO twin detectors in Louisiana and Washington state recorded a signal that would change everything. It was a distinctive chirp, a rising frequency that culminated in a final massive burst of energy. It was the sound of two black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. For the first time in human history, we had directly heard the cosmos. As physicist Kip Thorne, one of LIGO founding fathers, eloquently put it, with this discovery, we humans are embarking on a marvelous new quest, the quest to explore the warped side of the universe, objects and phenomena that are made from warped spacetime. Colliding black holes and gravitational waves are our first beautiful examples. The information encoded in these waves is a treasure trove for astrophysicists. By analyzing the specific shape and frequency of the signal, scientists can decipher the story of the cataclysm that created it. The waves carry a precise fingerprint of the objects involved, their masses, their spins, and their final orbits before merger. It's like being a cosmic detective. From a mere vibration, we can reconstruct the entire history of a billion-year-old dance that ended in a violent embrace. This new sense allows us to study black holes directly, even when they are completely dark and invisible to telescopes. We can probe the extreme nature of matter in neutron-star collisions, events that are also thought to be the cosmic forges where heavy elements like gold and platinum are created and scattered across the galaxy. This breakthrough forces us to ask an exhilarating question: what else will we hear? Gravitational wave astronomy is in its infancy, but it has already thrown open a new window on the universe, one that is completely independent of light. What other hidden engines are out there, vibrating the space-time around us? Could we detect the remnant rumble from the Big Bang itself, the primordial gravitational waves that would reveal the universe's first moments? Might we find evidence of cosmic strings, those hypothetical defects in space-time, snapping and sending waves across the eons? Or perhaps we will hear the signature of something entirely unexpected, a phenomenon we haven't even dreamed of yet. Each new chirp, each new ripple detected, is a direct message from the warped side of the universe, confirming that space-time is not a passive backdrop, but an active, dynamic participant in the ongoing drama of the cosmos. Now we've seen how immense cosmic events like colliding black holes send ripples through space-time. But what about the most fundamental building blocks of reality? What gives those building blocks their substance in the first place? This brings us to an engine that operates on the smallest of scales, but whose influence echoes throughout the entire cosmos: the Higgs field. This is the remarkable mechanism that endows fundamental particles with mass. And since mass is the primary sculptor of spacetime, the Higgs field is, in a very real sense, the ultimate source of gravity's raw material. Without it, the universe would be a formless, weightless void, with no planets, no stars, and no curvature to create the beautiful structures we see today. To understand how this works, we need to step away from the idea of empty space. According to quantum field theory, every particle is actually an excitation, a tiny vibration, in its own unique field that permeates all of reality. The electron field, the quark field, these are everywhere, and then there is the Higgs field. Imagine this field not as empty nothingness, but as a vast, invisible ocean of cosmic molasses that fills every cubic inch of the universe. Most fundamental particles, like electrons and quarks, have to swim through this molasses. This interaction is what we experience as mass. The more a particle interacts with the Higgs field, the more resistance it feels, and the heavier it is. A top quark, for instance, interacts very strongly and is extremely massive. A photon, the particle of light, doesn't interact with the Higgs field at all. It zips through the molasses completely unimpeded, which is why it is massless and always travels at the speed of light. A wonderful analogy for this is to picture a famous celebrity trying to move through a crowded room. As soon as they enter, people recognize them, gather around, and try to get their attention. This crowd of admirers clings to the celebrity, slowing their progress and making it much harder for them to move across the room. That difficulty, that resistance to acceleration, is exactly what mass is. The celebrity's interaction with the crowd gives them a kind of social inertia. Now, imagine an unknown person walking through that same room. Nobody pays them any mind. They can move quickly and easily from one side to the other. They have very little interaction with the crowd, and thus very little effective mass. In this metaphor, the people in the room represent the Higgs field, and the different individuals moving through it are the various fundamental particles. For decades, this was a brilliant but unproven theory. The final, crucial piece of evidence arrived in 2012, when the monumental ATLAS and CMS experiments at CERN Large Hadron Collider announced the discovery of the Higgs boson. It's important to understand what this boson is. It's not the field itself, but a tiny, localized ripple in the Higgs field. Think of the field as that ocean of molasses. If you were to give it a powerful enough splash, which is exactly what the LHC does by smashing protons together at nearly the speed of light, you can create a brief, detectable wave in that molasses. The detection of that wave, the Higgs boson, was our direct confirmation that the molasses-like field itself is real and pervades the entire universe. It was the final piece of the standard model of particle physics, a triumph of human prediction and ingenuity. Now, consider the profound implications of this. The Higgs field doesn't just give particles mass, it ultimately dictates the architecture of the universe. Without it, electrons would have no mass. Without mass, they wouldn't be captured by atomic nuclei to form stable atoms. There would be no chemistry, no solid matter, no structures of any kind. The universe would be a frenetic soup of massless particles zipping around at the speed of light, unable to clump together to form stars or galaxies. There would be no significant mass to create the deep gravitational wells that curve spacetime. The cosmos would be flat, featureless, and utterly unrecognizable. The Higgs field, by giving mass to the fundamental particles, provides the very substance that allows gravity to act as the great architect of the cosmos. This connection inevitably leads to a tantalizing line of thought. The strength of the Higgs field and the specific masses it gives to particles seem to be fixed by nature. But what if they were different? What if the Higgs field were slightly stronger or weaker? If it were stronger, particles would be heavier. Protons and neutrons might be too massive to form, or atoms might collapse in on themselves. If it were weaker, particles might be too light, preventing the formation of the complex structures necessary for life. The specific value of the Higgs mass appears to be yet another example of the delicate fine-tuning we see throughout physics, a value that allows for a universe that can host galaxies, planets, and curious beings like us who can ponder its existence. This deep connection between the quantum world of the Higgs field and the large-scale curvature of spacetime is a powerful hint of a grander unification, a theory of everything that would seamlessly weave together the rules of the very small with the geometry of the very large. But if the Higgs field gives particles the mass that allows them to shape spacetime, what then sets the direction for this entire cosmic drama? Why does the universe evolve in one particular way, from a state of exquisite order to one of increasing disorder, and never the other way around? This brings us to a profoundly different kind of engine, one that operates not through force or curvature, but through probability and information. It is the relentless, irreversible drive of entropy, governed by the second law of thermodynamics, and it carves the arrow of time itself into the very fabric of spacetime. This isn't just a law about steam engines or chemical reactions. It is a fundamental principle that dictates the ultimate fate of the entire cosmos, from the smallest particles to the largest galactic superclusters. At its heart, entropy is a measure of disorder, a count of the number of ways the microscopic components of a system can be rearranged without changing its overall appearance. A highly ordered state, like a perfectly stacked house of cards or a pristine sandcastle on a beach, has very low entropy. There are only one or two ways to arrange it that still look like that specific structure. But a disordered state, like that same deck of cards scattered randomly across a table or the sandcastle washed away by the tide, has incredibly high entropy. There are trillions upon trillions of ways for the cards to be scattered or for the sand grains to be arranged that all just look like a mess. The second law of thermodynamics states that the total entropy of a closed system, like our universe, always increases over time. It never decreases. The universe has a natural tendency to evolve from states of lower probability to states of higher probability, from order to disorder. A beautiful way to visualize this is to think of a tightly wound spring, like the one inside a mechanical clock. When it's fully wound, it's in a state of high order and potential energy, a low entropy state. It's wanting to unwind. As time passes, the spring slowly uncoils, releasing its energy, until it reaches a state of equilibrium where it's completely relaxed. This is its high entropy state. It has dissipated its energy, and it has no further tendency to change. The universe is doing the very same thing on a cosmic scale. It began in an extraordinarily special, low entropy state at the Big Bang, a state as ordered and unlikely as a perfectly wound spring or a deck of cards sorted by suit and number. Ever since that initial moment, it has been unwinding, its entropy increasing, driving all the processes we see. Stars burning, galaxies forming, and life itself evolving. We remember the past and not the future because the past is where the entropy was lower. The arrow of time is fundamentally an arrow of increasing disorder. The physicist Sean Carroll has eloquently explored this deep connection, explaining that time's arrow emerges directly from those special initial conditions. He points out that the laws of physics themselves are almost entirely time-symmetric. They work just as well running forward as backward. The equations don't have a built-in past or future. So why do we only ever see eggs scrambling and never unscrambling? Why do we see smoke dispersing from a fire and never collecting back into a log? It's not because it's physically impossible for all those particles to randomly reverse their paths. It's because it is astronomically, mind-bogglingly improbable. The universe started with all its order concentrated in one place, and it has been spreading out and winding down ever since. Our perception of the flow of time is our experience of the universe moving from a state of low probability to high probability. This concept becomes even more fascinating when we apply it to the most extreme objects in spacetime, black holes. In the 1970s, a young physicist named Jacob Bekenstein made a revolutionary proposal that was initially met with skepticism, even by Stephen Hawking. Bekenstein suggested that black holes must have entropy. This was a bizarre idea because entropy is related to disorder and the number of possible internal states a system can have. But a black hole was thought to be incredibly simple. According to the classical no-hair theorem, a black hole can be completely described by just three properties: its mass, its electric charge, and its spin. It seemed to be the most ordered, lowest entropy object imaginable. But Bekenstein realized that when you throw something with high entropy into a black hole, it vanishes from the observable universe. If the black hole itself couldn't have entropy, this would be a way to violate the second law. You could permanently decrease the total entropy of the universe by throwing messy things into a black hole. He argued that the black hole's entropy must increase to compensate. Stephen Hawking initially dismissed this but soon performed his own calculations, leading to his famous discovery of Hawking radiation. He found that not only do black holes have entropy, but their entropy is proportional to the surface area of their event horizon, not to their volume. This was a shocking result. In everyday life, the entropy of a system, like the air in a room, is proportional to its volume, the amount of space it takes up. But for a black hole, all that matters is the area of its boundary. This profound insight helped give birth to the holographic principle, the idea that all the information describing the three-dimensional volume inside a black hole might actually be encoded on its two-dimensional surface, like a cosmic hologram. The entropy of a black hole is a measure of the hidden information trapped within it, and it represents the ultimate fate of disorder in our universe. This leads to a truly spectacular and humbling question about the far, far future. As the universe continues to expand and accelerate under the influence of dark energy, and as black holes eventually evaporate over countless eons via Hawking radiation, what is the final state? The ultimate high-entropy fate seems to be a universe that has reached maximum equilibrium, a state physicists call the heat death. In this distant era, the temperature will be uniformly cold across all of space, all energy will be evenly distributed, and no further work will be possible. It will be the cosmic equivalent of that fully unwound spring, a quiet, static, and eternal state of perfect disorder. There will be no galaxies, no stars, no light. Just a thin, cold soup of particles drifting endlessly apart. The arrow of time, in a sense, will cease to have meaning because there will be no further processes to drive it. No clocks will tick, and no consciousness will be around to perceive its passage. Yet, even in this bleak picture, mysteries remain. Could entropy ever be reversed, even on a local scale? The laws of physics don't strictly forbid it. They just make it incredibly unlikely. Over an infinite amount of time, in an infinite universe, quantum fluctuations might occasionally conspire to create a local decrease in entropy, a temporary bubble of order arising spontaneously from the chaos. Some cosmological theories even suggest that such a fluctuation could, in principle, trigger a new Big Bang, giving birth to an entirely new universe from the ashes of the old one. While this remains highly speculative, it highlights the deep and enduring connection between the flow of time, the growth of disorder, and the very geometry of spacetime itself, showing us that the universe's story is written not just in space and mass, but in the irreversible and majestic unfolding of time. So we've seen how the relentless growth of entropy carves the arrow of time into the cosmos, guiding the universe from order to disorder. But what about the connections that seem to defy time and space altogether? What if the universe is bound together by threads so strange and profound that they challenge our very understanding of locality and reality itself? This brings us to one of the most bewildering and beautiful phenomena in all of physics: quantum entanglement. Imagine two particles, born together from a single event or interacting in just the right way, becoming so deeply linked that their fates are forever intertwined. They could be separated by the width of an atom or the breadth of a galaxy. It makes no difference. The moment you measure a property of one, say, its spin or polarization, the other particle, instantaneously and with no possible delay, snaps into a corresponding state. It's as if they are not two separate entities, but two parts of a single, unified whole, communicating faster than the speed of light in a way that seems to break all the classical rules of causality. Albert Einstein was deeply troubled by this implication of the quantum theory he helped to create. He could not accept that reality could be non-local, that an action in one place could immediately influence something in another without any signal passing between them. In a famous paper with his colleagues Boris Podolsky and Nathan Rosen, he argued that this spooky action at a distance, as he derisively called it, was proof that quantum mechanics must be an incomplete theory. He believed there must be some hidden variables, some deeper layer of reality we hadn't yet discovered, that would restore a sensible, local universe where objects are only influenced by their immediate surroundings. For decades, this was a philosophical debate, a thought experiment about the nature of reality. But then, in the 1960s, a physicist named John Bell devised a way to test it. His theorem provided a mathematical framework to distinguish between a universe with hidden local variables and one where quantum entanglement is real and truly non-local. When experiments were finally conducted, the results were unequivocal. Einstein was wrong. The universe does permit this spooky action. The particles are genuinely connected in a way that transcends space, as if the vast distance between them simply doesn't exist for their shared quantum state. A simple metaphor can help illustrate this profound connection, even if it can't fully capture its weirdness. Imagine you have two magical coins, and you seal one in a box on Earth and launch the other on a rocket to a distant star system light years away. You haven't looked at either coin yet. According to classical logic, each coin has a definite state. It's either heads or tails, from the moment they are separated. But in the quantum world, that's not how it works. Until the moment you open one box, neither coin has a definite state. They exist in a blurred, probabilistic superposition of both heads and tails simultaneously. The act of opening the box on Earth and seeing, say, heads, doesn't just reveal the state of that coin. It instantly forces the coin light years away to become tails. The information about the outcome seems to be communicated instantaneously, defying the cosmic speed limit set by light. This isn't just a theoretical curiosity. It's a phenomenon that has been experimentally verified again and again, and it forms the basis for emerging technologies like quantum computing and quantum cryptography. But this leads to a truly revolutionary and modern question. If entangled particles are instantaneously connected across vast distances, how does that connection actually work? What is the physical mechanism that bridges the gap? This is where the world of quantum weirdness and the world of spacetime geometry might spectacularly collide. In recent years, a fascinating and profound idea has emerged from the frontiers of theoretical physics, most notably from the work of Juan Maldacena and Leonard Susskind. They proposed a duality known as ER equals EPR. Let's unpack that. ER refers to Einstein-Rosen bridges, which are the formal name for wormholes, theoretical tunnels through spacetime that could, in principle, connect two distant points. EPR refers to the Einstein-Podolsky-Rosen paper that first highlighted the paradox of entanglement. This daring conjecture suggests that these two concepts, once thought to be completely separate, might be one and the same. It proposes that every pair of entangled particles is not actually connected by some mysterious, invisible signal flying through space, but is instead linked by a microscopic wormhole, a tiny, Planck-scale bridge in the very fabric of spacetime itself. Think about that for a moment. The spooky action at a distance that so troubled Einstein might not be action through space at all. It might be action that takes a shortcut through spacetime geometry. The entanglement, the deep quantum connection between two particles, could be physically embodied by an ultra-tiny wormhole stitching them together. This doesn't mean we could ever use this connection to send a faster-than-light message or travel instantly across the galaxy. These microscopic wormholes are undoubtedly unstable and unimaginably small. But it does provide a breathtakingly geometric picture of quantum correlation. It suggests that the phenomenon of entanglement, which seems to defy our classical notions of separation, might be the first hint that spacetime itself is not the fundamental stage of the universe, but a structure that emerges from a vast, underlying network of quantum connections. This idea forces us to consider a possibility that turns our understanding inside out. We normally think of space as the container within which things like particles and fields exist and interact. But what if that's backwards? What if space itself is a secondary phenomenon, a kind of illusion that arises from something deeper? What if the fundamental ingredients of the universe are not particles located in space, but rather an immense web of quantum information, countless particles entangled with each other in a complex, non-local network? In this view, the geometry of spacetime, with its curves and distances, its gravitational wells and its expansion, is not primary. It is a translation of the quantum information stored in these entangled connections. The smooth, continuous spacetime of general relativity would be a kind of holographic projection, a large-scale approximation of a reality that is ultimately discrete and informational. The fabric of the cosmos, in its most fundamental form, might be woven not from strings or fields, but from relationships, from entanglement itself. So, could it be that this bizarre quantum connection is actually the invisible glue that holds space together? Could the geometry we experience every day, the distance from your hand to your coffee cup, the vast expanse between stars, be built from countless threads of entanglement stitching every point in the universe to every other point? It's a staggering thought, one that bridges the two great pillars of 20th century physics that have so stubbornly resisted unification. General relativity gives us the stage, the beautiful, dynamical geometry of spacetime. Quantum mechanics gives us the actors, the particles and their strange, probabilistic behaviors. The ER equals EPR conjecture, and ideas like it, suggest that the actors and the stage might be made of the same stuff, and that the most fundamental property of the universe might not be substance, but connection. Now, if the bizarre connections of quantum entanglement hint at the very fabric of spacetime being woven from information, we must ask, how did this grand tapestry get its start? What primordial engine could have taken a universe of infinite potential and set it on the specific course that led to us? This brings us to one of the most pivotal ideas in all of cosmology, the theory of cosmic inflation. Imagine the universe not even a full second after its birth, an unfathomably hot, dense, and chaotic fireball. According to the standard Big Bang model, this infant cosmos should have been riddled with extreme irregularities, with some regions vastly denser than others. It should have been curved and contorted by the very energy that filled it. And yet, when we look out at the universe today, across billions of light years, we find something astonishingly different. The cosmos is, on the largest scales, incredibly smooth and flat. The temperature of the cosmic microwave background radiation, the leftover glow from the Big Bang, is uniform to within 1 part in 100,000. How did such perfect smoothness emerge from such primordial chaos? The answer, proposed by physicist Alan Guth in the early 1980s, is a breathtakingly brief but monumentally powerful event called inflation. Guth realized that the universe could have undergone a period of hyper-exponential expansion, doubling in size again and again, within a tiny fraction of a second. This wasn't the steady, stately expansion we see today. This was a violent, supercharged stretching of the very fabric of spacetime itself, driven by a mysterious scalar field known as the inflaton field. Think of this field as a form of energy temporarily trapped in a peculiar state that endowed empty space with a powerful negative pressure, acting like a sort of anti-gravity. For a fleeting moment, roughly from 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 78. That's a number so large it's difficult to comprehend taking something a billion times smaller than a proton and blowing it up to the size of a grapefruit in an instant. A perfect analogy for this is to take a partially inflated balloon covered in wrinkles and creases. These wrinkles represent the initial chaos and unevenness of the early universe. Now imagine blowing up that balloon at an incredible, unimaginable speed. As it expands rapidly, the surface of the balloon stretches, and all those small wrinkles are smoothed out into a nearly perfect, flat, and uniform surface. This is precisely what the inflationary epoch did to our cosmos. It took a tiny, tangled, and potentially curved patch of the primordial universe and stretched it so enormously that it became the vast, smooth, and geometrically flat observable universe we inhabit today. It erased the initial imperfections, providing an elegant explanation for the remarkable large-scale uniformity we observe. As Alan Guth himself noted, inflation offers a compelling solution to the horizon problem, the puzzle of how regions of the universe now far apart, which could never have been in thermal contact given the finite speed of light, manage to reach the same exact temperature. But inflation did something even more miraculous than just ironing out the wrinkles. It also created the seeds for all future structure. While the inflaton field was driving this tremendous expansion, it wasn't completely static. Like all quantum fields, it was subject to tiny, unpredictable fluctuations, miniature ripples in its energy value. These quantum jitters, these microscopic irregularities, were happening on a scale smaller than atoms. But then, inflation struck. In that frantic period of hyper-stretching, these infinitesimal quantum fluctuations were blown up to astronomical sizes. They were imprinted directly onto the fabric of spacetime as tiny differences in density, some regions ever so slightly denser than others, After inflation ended, and the energy of the inflatoned field decayed into the hot soup of particles of the standard Big Bang, gravity got to work on these imprinted blueprints. Over billions of years, the slightly denser regions had a stronger gravitational pull, slowly drawing in more and more matter. They became the gravitational wells that eventually grew into the first stars, the galaxies, the galaxy clusters, and the vast cosmic web we see mapping the universe today. The grand tapestry of existence, with its brilliant galaxies and immense voids, began as nothing more than quantum noise, magnified by the most powerful engine the universe has ever known. This incredible success naturally leads us to some of the most profound questions we can ask. What exactly was the inflatoned field? Was it a fundamental field, a cousin to the Higgs field, that we might one day detect? Or was it something more exotic? And what triggered this monumental event to begin? What flipped the switch that started this incredible expansion, and what caused it to stop so abruptly? The answers to these questions are still hidden in the realm of theoretical physics, but they point toward ideas at the very frontier of knowledge, perhaps involving grand unified theories or even concepts from string theory. Furthermore, if our universe underwent inflation, could the same process happen elsewhere? Many versions of inflationary theory naturally lead to the concept of eternal inflation and a multiverse. The idea is that once inflation starts, it may never truly stop everywhere. Instead, the inflatoned field could decay in some regions, like ours, creating isolated, bubble universes with their own distinct properties and physical laws, while the overall inflationary background continues to expand forever, endlessly giving birth to new bubbles. Our entire cosmic history, from the Big Bang to the present day, might just be a single event within an infinitely larger, eternally inflating meta-universe. This concept forces us to confront the staggering possibility that the forces that shaped our reality, the strength of gravity, the mass of the electron, the value of the cosmological constant, might not be fundamental, immutable laws, but rather local bylaws, the outcome of a random quantum fluctuation during our particular bubble's inflation. It suggests that the primordial forces that crafted our cosmic environment might be just one set of possibilities in a much vaster and more diverse cosmic landscape, a thought that is as humbling as it is exhilarating. But if our universe's smooth beginning was set by the explosive stretching of inflation, what is the true nature of the stage it was stretching? We've been exploring spacetime as a four-dimensional fabric, 3 of space and 1 of time, but what if this is merely the portion of reality we can perceive? What if our entire cosmos is just a single slice of something vastly larger? A mere membrane floating within a higher dimensional reality. This is not science fiction. It is a serious, compelling frontier of theoretical physics known as brain cosmology, and it suggests that the most fundamental engines shaping our universe may be operating in dimensions hidden from our view, making our familiar spacetime a fascinating special case. The idea springs primarily from string theory, the ambitious framework that proposes the fundamental constituents of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. For the mathematics of string theory to work consistently, it requires more than the 4 dimensions we experience. It demands 10, or even 26 dimensions of spacetime. This immediately raises an obvious question. If these extra dimensions exist, where are they? Why don't we see them, walk through them, or perceive them in any way? One captivating solution is that these dimensions are not expanded and vast like our own. They are compactified, curled up into a space so incredibly tiny, on the scale of the Planck length, that they are completely invisible to us, much like a garden hose appears as a one-dimensional line from a distance, but upon closer inspection reveals a second, circular dimension curled around. Circumference. Brain cosmology takes this a step further with a truly mind-bending proposition. It suggests that our entire four-dimensional universe could be a three-dimensional membrane shortened to brain, embedded within a higher dimensional bulk space. In this view, the particles that make up our world, like electrons and quarks, are like tiny waves or vibrations trapped on the surface of this brain. They are stuck here, unable to leave, which is why we only ever perceive three dimensions of space and one of time. But gravity, the curvature of spacetime itself, might be different. It might be the one fundamental force that is not confined to our brain. It could be a force that permeates all dimensions, leaking out into the higher dimensional bulk. This could provide a stunning explanation for one of physics' deepest puzzles. Why is gravity so phenomenally weaker than the other fundamental forces? The electromagnetic force is a trillion times stronger. It's as if you compared the power of a single hydrogen bomb to the gentle push of a feather. If gravity's influence is spreading out into these extra dimensions, its strength in our world would be dramatically diluted, like a whisper fading in a vast cathedral. What we perceive as weakness might simply be dilution. To visualize this, imagine a world of ants living on the surface of a large, taut sheet of paper. This sheet is their entire universe. They can crawl forward, backward, left, and right, but the concept of up is meaningless to them. They are completely unaware of another sheet of paper floating just a millimeter above their heads in the third dimension, hosting its own entire civilization of ants. Now, imagine a tiny grain of sand falls from the upper sheet and lands on the lower one. From the perspective of the ants on the lower brain, that grain of sand simply appeared out of nowhere, a mysterious event they cannot explain within their two-dimensional physics. In this analogy, we are the ants. Our three-dimensional world is that sheet, and we are oblivious to other brains that might be hovering nearby in a higher dimensional space. Events in that bulk space could occasionally intrude on our world, appearing as inexplicable phenomena. This idea was spectacularly refined by physicists Lisa Randall and Raman Sundaram in the late 1990s. They proposed a model where the extra dimension isn't small and curled up, but large and even infinite. How could we not notice an infinite extra dimension? Their brilliant insight was that this dimension could be warped. They imagined our universe as a brain sitting at one end of a five-dimensional bulk, where the geometry of that bulk is intensely curved, like a steep mountain slope. The force of gravity would be naturally much stronger on the other end of this warped dimension, but its influence would diminish exponentially as it travels along the warped geometry to reach our brain. To us, gravity would appear weak, providing an elegant and geometric solution to the hierarchy problem without needing to hide the dimensions away. This warped geometry isn't just a mathematical curiosity. It could have observable consequences, such as the production of miniature black holes in powerful particle colliders or the presence of gravitons, the hypothetical particles of gravity, with specific, detectable properties. The implications of living on a brain are profound and could reshape our understanding of the cosmos's greatest mysteries. Could dark energy, the force accelerating the universe's expansion, be the subtle influence of a neighboring brain in the bulk, gently pushing against our own? Could the Big Bang itself have been triggered by a cataclysmic collision between our brain and another? Perhaps the mysterious dark matter that holds galaxies together is simply ordinary matter from a parallel brain universe, whose gravity, bleeding through the bulk, is the only thing we can detect. Each of these ideas is an active area of research, showing how this shift in perspective opens up entirely new avenues for explaining the fundamental properties of our reality. This forces us to confront a deeply philosophical question about the limits of our perception. Our entire scientific understanding is built on the data collected by our five senses and the instruments we've built to extend them. But what if our senses are inherently limited, not by the quality of our technology, but by the very nature of our existence? We are three-dimensional creatures, patterns of vibrations confined to a three-dimensional membrane. Is it any wonder we cannot directly perceive a fourth spatial dimension? It would be like a character in a painting trying to look up from the canvas to see the museum gallery. The very tools we use to explore the universe, the particles we are made of, are bound by the same rules, trapping us within this slice of reality. The true nature of the cosmos might be a magnificent, multi-dimensional structure, and we are merely experiencing a single, fascinating shadow of it. Now, if the universe's grand structure might be a projection from a boundary or a membrane in a higher dimensional space, we are forced to ask an even more fundamental question about the nature of nothingness itself. What is the true energy of empty space? This brings us to a profound and deeply troubling conflict at the very heart of modern physics. A problem so severe it represents the largest gap between prediction and observation in the entire history of science. We are talking about vacuum energy, the lowest possible energy state of a quantum field, and its catastrophic, unexplained failure to warp the cosmos into non-existence. This isn't just a minor puzzle. It is a glaring warning sign that our two most successful theories, quantum mechanics and general relativity, are fundamentally at odds when it comes to describing the void. Let's start with what quantum theory tells us about empty space. We've already explored how the vacuum is not truly empty, but is instead a seething, bubbling foam of virtual particles constantly flickering in and out of existence. Every point in space, according to quantum field theory, is a site of this relentless activity. Each of these quantum fields, the electron field, the quark field, the photon field, has a ground state, a lowest possible energy level, even when no real particles are present. This is the zero-point energy of the vacuum. When you add up all the contributions from every possible frequency of every possible quantum field that exists, you get a number for the vacuum energy density. The calculation is straightforward, but the result is nothing short of mind-boggling. This theoretical energy density should be enormous, around 120 orders of magnitude larger than the energy density we actually observe from the cosmological constant driving the universe's acceleration. That's a 1 followed by 120 zeros. It is a number so ludicrously large that it has no analogy in the physical world. It is perhaps the worst prediction ever made. To grasp the implications of this, we need to recall Einstein's greatest insight, that energy curves spacetime. All forms of energy, including the energy of the vacuum, should create gravity. This immense vacuum energy density, if it were real, would generate a correspondingly immense curvature of spacetime. The repulsive gravity from this energy would be so powerful that it would have blown the universe apart in the tiniest fraction of a second after the Big Bang. Stars, planets, and atoms could never have formed. The universe would be a vast, empty, featureless void, expanding so rapidly that nothing could ever coalesce. And yet, here we are. Our universe exists with its galaxies and its life, and the observed vacuum energy is not a number with 120 zeros. It is a very small, positive value that only began to dominate the expansion of the universe a few billion years ago. This colossal discrepancy is known as the cosmological constant problem, and it stands as a monumental challenge to our understanding of physics. The great physicist Steven Weinberg, who helped unravel the mysteries of the Standard Model, called this problem the one real crisis we have in theoretical physics. He and others have wrestled with it for decades. How can the vacuum be so energetic on paper, and yet so calm in reality? A powerful metaphor is to think of the vacuum as a deep, calm ocean on a windless day. On the surface, everything appears serene and flat. But if you could feel the water beneath the surface, you would discover a world of powerful currents and immense pressures. Quantum field theory is describing those powerful, chaotic undercurrents, but our astronomical observations are only seeing the serene, flat surface. The mystery is why the surface is so placid when everything beneath it suggests it should be a raging maelstrom. So, where did we go wrong? Theorists have proposed several compelling, though as yet unproven, solutions. One elegant idea is supersymmetry, a theoretical extension of the Standard Model. Supersymmetry proposes that for every known particle, every electron, every quark, there exists a supersymmetric partner particle. The beautiful mathematical property of such a theory is that the contributions to the vacuum energy from a particle and its superpartner could be exactly opposite, perfectly canceling each other out. The positive energy from the dance of electrons could be precisely negated by the negative energy from their hypothesized selectron partners, leaving a net vacuum energy of zero or very near zero. This would solve the problem neatly. However, despite extensive searches at the Large Hadron Collider and other experiments, no evidence for these superpartner particles has been found. If supersymmetry exists in nature, it must be at energy scales higher than we have so far been able to probe, leaving the puzzle unresolved. Another, more philosophical approach is the anthropic principle. This line of reasoning suggests that the value of the vacuum energy isn't determined by a fundamental law of physics, but is instead a random variable that could take on different values in different parts of a vast multiverse. In most of these universes, the vacuum energy is indeed enormous, and those universes expand too quickly or collapse too rapidly to ever form stars or life. But in a vanishingly small number of universes, by pure chance, the vacuum energy is very small. It is only in these rare, life-permitting universes that observers like us can arise to measure it and wonder about its value. In this view, the question, "Why is the vacuum energy so small?" has a simple, if unsettling, answer. Because if it weren't, we wouldn't be here to ask the question. While this avoids the need for a precise cancellation mechanism, it moves the explanation from the realm of predictive physics to one of environmental selection, a shift that many physicists find deeply unsatisfying. Ultimately, the cosmological constant problem is more than just a calculation error. It is a direct confrontation with the limits of our knowledge. It screams that we are missing a crucial piece of the puzzle, a deeper theory that successfully merges the quantum world with the gravitational one. Perhaps our understanding of quantum field theory is incomplete when applied to the vacuum on the scale of the entire universe. Maybe the vacuum energy gravitates in a different way than ordinary energy sources, a possibility explored in some modified gravity theories. Or it could be that the vacuum energy is indeed large, but its gravitational effect is somehow shielded or screened from our large-scale perspective, like a force that cancels itself out over long distances. Each of these ideas is a shot in the dark, an attempt to resolve a crisis that has persisted for over half a century. It forces us to humbly acknowledge that the void, the very definition of nothing, remains one of the greatest and most active frontiers in our quest to understand the invisible engines of the cosmos. But what if the very fabric of spacetime can do more than just bend? What if it can also twist? For over a century, Einstein's general relativity has given us an incredibly powerful and accurate description of gravity as the curvature of spacetime. It is a masterpiece of physics, but it might not be the complete picture. Just as a rope can be bent into a curve or twisted along its length, some of the most intriguing alternative theories of gravity propose that spacetime itself could possess a property known as torsion, a kind of intrinsic twisting that adds a whole new layer of complexity to how matter and geometry interact. This idea isn't new. It dates back to the 1920s, just a few years after Einstein published his seminal work. The brilliant French mathematician Élie Cartan, a pioneer in differential geometry, realized that the mathematical framework Einstein used could be naturally extended. In Einstein's theory, the curvature of spacetime is directly tied to the energy and momentum of matter. Cartan proposed that another geometric quality, torsion, could be directly tied to something else, the quantum spin of particles. Think of spin not as a literal ball rotating, but as a fundamental, intrinsic form of angular momentum that every electron, quark, and other fundamental particle carries, much like a tiny magnetic arrow. In standard general relativity, this spin property is treated as just another form of energy that contributes to curvature. But in the Einstein-Cartan theory, spin does something more profound. It actually twists the local fabric of spacetime around it. A simple analogy can help illustrate the difference. Imagine you have a simple, flexible rubber hose. Now, bend it into a smooth, graceful arc. This bending represents the kind of curvature described by Einstein's theory. It's how a planet or a star warps the space around it, creating the gravitational wells that guide the motion of other objects. Now, take that same hose and twist it along its length. Notice how this twisting doesn't just change its overall shape. It puts an internal stress on the material, a kind of corkscrew tension that is fundamentally different from a simple bend. This twisting is the essence of torsion. In regions of space filled with matter that has a high density of spin, like the incredible densities inside a neutron star or in the very early universe, this torsional stress could become a significant player, subtly altering the predictions of how gravity behaves. For decades, these ideas remained largely in the realm of mathematical curiosity. But in recent years, physicists have begun to explore whether torsion could provide elegant solutions to some of the most stubborn problems in cosmology. One fascinating possibility is that torsion might offer an alternative explanation for the phenomenon we attribute to dark matter. We observe that galaxies rotate too quickly for the visible matter within them to hold them together, leading us to infer the existence of vast halos of invisible dark matter. But what if, instead, the collective gravitational influence of all the spinning particles within the galaxy creates a pervasive torsional field on cosmic scales? This twisting of spacetime could, in theory, provide an additional gravitational glue that holds fast-spinning galaxies together without needing to invoke any mysterious, unknown particles. It's a compelling thought that the answer to one of astronomy's greatest mysteries might not lie in some exotic substance, but in a deeper understanding of how the spin of known particles sculpts the geometry of the universe. Furthermore, torsion might hold the key to resolving one of the most troubling aspects of general relativity, the singularity. At the heart of a black hole, and at the very beginning of the Big Bang, Einstein's equations predict a point of infinite density and curvature, a place where the laws of physics as we know them simply break down. Most physicists view this as a sign that the theory is incomplete, that it must be replaced by a quantum theory of gravity in these extreme regimes. Intriguingly, in some models incorporating torsion, this problem simply vanishes. The equations show that the twisting effect of spacetime, driven by the spin of particles, can create a repulsive force that becomes overwhelmingly powerful at extremely high densities. This repulsion could prevent matter from collapsing into an infinitely dense point, instead causing it to bounce and creating a universe without a true singularity. This opens up breathtaking possibilities, like the potential for our Big Bang to have been the result of a prior universe collapsing and then bouncing back, thanks to the repulsive power of torsional gravity. This exploration into alternative theories like Einstein-Cartan is not an attempt to dethrone general relativity, which remains one of the most successfully tested theories in all of science. Instead, it enriches our narrative, reminding us that our understanding of the cosmos is still evolving. It introduces a healthy diversity of thought into gravitational physics, challenging us to ask, is our current model the final word, or is it a brilliant approximation of a deeper, more complex geometric reality? The universe has consistently proven to be more imaginative than we are, and the possibility that space-time can twist as well as bend is a thrilling reminder that the invisible engines of the cosmos may still have profound secrets left to reveal. But what if the very idea of a three-dimensional universe is an illusion? What if all the information needed to describe every star, every planet, and every one of us could be perfectly encoded on a vast, two-dimensional surface surrounding us, like some kind of cosmic movie screen? This is the breathtaking and deeply counterintuitive proposal of the holographic principle, an idea that radically suggests that spacetime itself is not fundamental, but is instead a projection, an emergent phenomenon that arises from a deeper, lower-dimensional reality. It's a concept that forces us to reconsider the very nature of what is real, proposing that the rich, three-dimensional world we experience might be akin to a magnificent hologram. To begin to grasp this, let's consider an ordinary hologram, like the kind you might see on a credit card or a banknote. That shiny, two-dimensional surface doesn't just contain a flat picture. When you shine a laser through it or tilt it in the light, it projects a fully three-dimensional image that you can look around. All the information needed to create that seemingly solid, three-dimensional object is contained entirely on the two-dimensional film. The holographic principle applies this same logic to the entire universe. It suggests that our seemingly solid, three-dimensional reality, with all its depth and volume, might be a projection from a two-dimensional surface that surrounds us at the farthest edges of the observable universe. In this view, every event that happens within the volume of space, every supernova explosion, every orbit of a planet, every thought in your mind, is actually encoded as intricate information on this distant, flat boundary. We are not living inside the universe so much as we are living within an image projected from its outer shell. This astonishing idea didn't emerge from pure speculation. It grew out of one of the most perplexing puzzles in theoretical physics, the black hole information paradox. When something falls into a black hole, it seems to vanish forever, taking all information about its properties with it behind the event horizon. This violates a sacred principle of quantum mechanics, which states that information can never be truly destroyed. In the 1990s, physicists like Leonard Susskind and Gerard T. Hooft began to explore a radical solution. They argued that when an object falls into a black hole, all the information that described it isn't actually lost inside the hole. Instead, it becomes encoded and scrambled across the black hole's two-dimensional event horizon, the surface of its point of no return. The horizon acts like that two-dimensional holographic film, storing the information in tiny, plank-sized pixels. As Susskind himself has said, this implies that the three-dimensional world is an image of data that can be stored on a two-dimensional projection, a realization that shakes the very foundations of our understanding of space and time. The mathematical framework that gives this idea incredible weight is known as the AD/CFT correspondence, first proposed by Juan Maldacena in 1997. This is a concrete, and in some cases proven, duality between two seemingly completely different kinds of physics. On one side, you have a theory of gravity operating in a hypothetical higher dimensional volume of space. On the other side, you have a conformal field theory, which is a quantum theory without gravity, that lives on the lower dimensional boundary of that volume. The miracle is that these two theories, operating in different numbers of dimensions, are mathematically completely equivalent. They are two different descriptions of the exact same underlying reality. This provides a powerful hint that the gravitational forces we experience in our three-dimensional world might actually be a manifestation of quantum processes playing out on a distant two-dimensional surface. Gravity and the very dimension of space itself may not be fundamental building blocks, but rather emergent properties that arise from a vast, complex network of quantum information. If this is true, the implications for our understanding of spacetime mechanics are nothing short of revolutionary. It could provide a beautifully simplified description of the universe. Describing the complex, warped geometry of spacetime in 3 dimensions, with all its black holes and gravitational waves, might be incredibly difficult. But if that same reality can be perfectly described by a quantum theory without gravity on a 2-dimensional surface, it could offer a far simpler and more fundamental way to understand the cosmos. The mind-bending laws of quantum mechanics and the curved landscape of general relativity, the 2 great pillars of physics that have stubbornly resisted unification for a century, might find their common ground not in a deeper theory of spacetime, but in a theory where spacetime isn't the main character at all. The true actors would be the quantum bits of information living on the boundary, and the universe we perceive would be their magnificent collective projection. This forces us to ask a question that ventures from the scientific into the deeply philosophical. What is the true nature of our reality if the space we move through and the time we experience are not fundamental? Are we, and everything we see, essentially a shadow on a wall, a phantom projection from the edge of existence? The holographic principle doesn't diminish the reality of our experience. The image is still real, the story is still compelling, but it does suggest that there is a far deeper layer of computation and information processing underlying the cosmos, a layer where the familiar concepts of location and distance may have no meaning at all. It challenges us to think of the universe not as a container of things, but as a network of relationships, a cosmic computation whose output is the breathtakingly realistic illusion of a 3-dimensional world. Now, let's journey even further back, to the very first moments after the Big Bang, when the universe was a seething, unfathomably hot plasma, cooling and changing state as it expanded at a phenomenal rate. Just as water freezing into ice can develop cracks and fissures as its molecular structure rearranges, the universe, as it underwent its own profound phase transitions, could have developed its own kind of cosmic cracks frozen into the very fabric of spacetime. These hypothetical relics are known as cosmic strings, and they represent a fascinating class of 1-dimensional defects, theoretical fossils from the universe's most violent infancy that could still be stretching across the cosmos today, acting as ultra-dense, gravitational filaments with the power to warp reality around them in extraordinary ways. Imagine the universe cooling from an initial state of perfect symmetry, where all the fundamental forces were unified into one. As it cooled, this symmetry broke, and different forces, like the strong nuclear force and the electromagnetic force, froze out, much like water molecules arranging themselves into the crystalline structure of ice. But this process might not have happened perfectly uniformly everywhere. In some regions, the new, lower energy state might have aligned one way, and in an adjacent region, it might have aligned another. Along the boundary between these 2 mismatched regions, a persistent flaw in the structure could have become trapped, a kind of scar in the cosmic order that simply couldn't smooth itself out. A cosmic string is exactly that, an infinitely long, incredibly thin scar in spacetime. A defect where the old, high-energy, symmetric state of the early universe got locked in place. Despite being thinner than a proton, a cosmic string would possess immense density, with a single inch of its length potentially containing more mass than Mount Everest, making it one of the most extreme objects conceivable. The gravitational influence of such an object would be unlike anything else in the universe. Because a cosmic string is a linear defect, it doesn't create a spherical gravitational well like a star or a black hole. Instead, it warps the space around it in a unique, conical fashion. Picture space as a flat, flexible sheet. A massive ball would create a deep, round depression. But a cosmic string would be like taking that sheet and cutting out a narrow, pizza slice-shaped wedge, then seamlessly stitching the edges back together. The result is that space becomes slightly conical around the string. This peculiar geometry leads to some incredible physical effects. For instance, if you were to travel in a perfect circle around a cosmic string, you would find that the total distance around it is less than 2 pi times the radius, a clear violation of everyday Euclidean geometry caused by the missing wedge of space. This warping would make cosmic strings potent gravitational lenses, but with a distinctive signature. While the gravity of a galaxy or a cluster of galaxies will smear the image of a distant background object into arcs or rings, a cosmic string would create a very different effect. A perfect, identical double image of a single galaxy or quasar, with no distortion or blurring, because the lensing would be perfectly linear. Even more bizarrely, the conical spacetime around a moving cosmic string could theoretically create closed time-like curves, regions where spacetime is so twisted that an object could travel on a path that brings it back to its own past, creating the potential for time loops. While the stability of such loops is a matter of intense debate, the mere possibility highlights the profound and strange influence these objects could have on the structure of reality itself. For cosmologists, these strings are more than just theoretical curiosities. They could have been the primordial seeds around which the entire cosmic web of galaxies formed. In the early universe, the immense density of a network of cosmic strings would have provided the initial gravitational nudges necessary to pull ordinary matter together, jump-starting the formation of the first stars and galaxies long before other processes could have taken hold. Their gravitational wake could have provided the blueprint for the vast filamentary structures we see in the universe today, the great walls and threads of galaxies that trace out the largest patterns in existence. While the inflationary theory has largely taken over as the leading explanation for the initial density fluctuations, some models intriguingly combine both ideas, with cosmic strings forming at the very end of the inflationary epoch, adding their own unique texture to the early universe. The pressing question, of course, is whether these spectacular relics actually exist. How could we ever hope to detect a filament so thin yet so massive? Astronomers have been searching for their unique imprints for decades. The most promising method is to look for their effect on the cosmic microwave background, the leftover radiation from the Big Bang. A cosmic string moving through the early universe would have created tiny, sharp ripples in this radiation, and next-generation telescopes are actively searching for this distinctive signature. Another approach is to use the fact that they could generate gravitational waves. Unlike the violent, chirping signals from black hole mergers, a cosmic string would potentially produce a continuous, steady hum of low-frequency gravitational waves as it oscillates, or if loops of string were to form and slowly evaporate. The precise timing of ultra-regular pulsars in our galaxy, used as a galaxy-scale gravitational wave detector, might one day pick up this faint, cosmic symphony played on strings of spacetime. The hunt for these cosmic fossils is a direct attempt to probe the highest energy scales imaginable, energies we could never hope to recreate in any particle collider on Earth. Finding even a single cosmic string would be like discovering a perfectly preserved dinosaur bone, offering us an unprecedented window into the universe when it was less than a second old, confirming the physics of grand unification and symmetry breaking. It would prove that the cosmos itself preserves its history not just in the arrangement of galaxies, but in the very topological defects etched into the foundation of reality, frozen remnants of a time when the entire universe was undergoing a change of state, locking its most dramatic moments into scars that might still stretch across the heavens. Now, after exploring cosmic strings and other relics from the universe's fiery birth, we arrive at a question that is perhaps the most personal and profound of all. Why does the universe seem so perfectly set up for us? We've seen how the laws of physics, with their specific constants and forces, create the conditions for galaxies, stars, planets, and ultimately, life. But what if this isn't a cosmic coincidence? What if it's the other way around? This line of thinking leads us to the anthropic principle, a concept that shifts the focus from the universe itself to the observers within it, suggesting that the very parameters of spacetime might be shaped by the necessity of our own existence. The core idea is elegantly simple, yet it carries deep philosophical weight. It's a principle of selection bias. Imagine you're a fish born in a pond. You might conduct a scientific study of your world and conclude that water is a fundamental, universal property of reality. It would never occur to you that your very presence as a water-breathing creature is what defines and limits your investigation. You cannot observe a universe without water because you couldn't exist there to make the observation. In the same way, we humans, as conscious observers, can only find ourselves in a universe that has the specific set of physical constants and laws that allow for our evolution. We are, in a sense, selecting for the universe we see, not the other way around. The physicist Brandon Carter, who formally coined the term Anthropic principle in 1973, framed it not as an explanation, but as a crucial constraint on our theories. He argued that what we can expect to observe must be restricted by the conditions necessary for our presence as observers. This idea gives us a powerful new lens through which to view some of the most nagging fine-tuning problems in cosmology. Take the cosmological constant, that mysterious energy of the vacuum we discussed earlier. The value we measure is astonishingly small, yet a straightforward calculation from quantum physics suggests it should be enormous. If it were even slightly larger than it is, the repulsive gravity would have been so powerful in the early universe that it would have blown matter apart before it could ever coalesce into galaxies and stars. There would be no planets, no chemistry, and certainly no life. The anthropic principle offers a different perspective. Perhaps the cosmological constant isn't a fixed, fundamental number set by a deep law. Perhaps it can vary from one region of reality to another. In that case, we shouldn't be surprised to find ourselves in a region, a universe, or a pocket where the value is exceptionally small. Because it is only in those rare, quiet corners of reality that observers like us can ever arise to ponder its value. Our existence itself is the evidence that we live in a universe with a cosmological constant suitable for life. This reasoning extends far beyond just one constant. The strength of gravity, the mass of the electron, the precise energy levels in the carbon atom that allow for the complex chemistry of life, all of these appear to be balanced on a razor's edge. It's a cosmic Goldilocks zone for physical laws, where everything is not too strong and not too weak, but just right. The force of gravity, for instance, is perfectly calibrated. If it were significantly stronger, stars would burn their fuel too quickly and collapse into black holes, never providing the stable, long-term warmth needed for life to evolve on a planet. If it were much weaker, matter would never have clumped together to form stars in the first place, leaving the universe a cold, dark, and eternal haze of dilute gas. The universe seems to be exquisitely fine-tuned, and the anthropic principle provides a framework for why that might be so without requiring a designer. It's not that the universe was made for us, it's that we are a product of a universe that happened to have the right ingredients. This line of thinking inevitably pulls our gaze toward one of the most speculative and magnificent ideas in all of science, the multiverse. If the anthropic principle is correct, it naturally suggests the existence of a vast ensemble of universes, each with its own unique, randomly determined set of physical laws and constants. In this cosmic landscape, most universes would be stillborn or barren, perhaps collapsing instantly or expanding into endless emptiness, or possessing forces too weak to ever bind atoms together. But in an incomprehensibly vast multiverse, every possible combination of physical parameters will be realized somewhere. By sheer probability, a tiny fraction of these universes will, by pure chance, have the perfect recipe for complexity and life. And in those universes, observers will eventually emerge, look around, and marvel at how perfectly tailored their world seems to be, never knowing about the infinite, lifeless failures that surround them. Our universe wouldn't be special. It would simply be the one we won the lottery to live in. This introduces a fascinating philosophical tension. Does the anthropic principle represent a Copernican revolution, humbling us by suggesting our universe is just one among countless others? Or does it ironically recenter us by making our conscious observation a fundamental part of the cosmic equation? It challenges the traditional goal of physics, to find a single, elegant, fundamental theory that predicts all constants with necessity. Instead, it proposes that some of these constants might be environmental, like the temperature of a planet, determined by local conditions rather than universal law. This isn't a surrender to mystery. It's a call for a broader kind of science, one that can explain the mechanism that generates this multiverse and the distribution of constants within it, such as the ongoing inflation we discussed earlier. It connects the immense, impersonal mechanics of spacetime directly to the most intimate fact of our own existence, weaving life itself into the grand tapestry of cosmic causality. But of all the strange and wondrous structures the universe can create, perhaps none is more bizarre than one that challenges our deepest assumptions about time itself. We are used to thinking of matter in phases: solid, liquid, gas, plasma states defined by how their atoms are arranged in space. But what if matter could also have a phase defined by its behavior in time? This is the revolutionary concept behind time crystals, a new phase of matter that doesn't just exist in space, but performs a constant, unwavering dance in time, a dance that continues forever without ever consuming a single drop of energy. It sounds like the dream of a perpetual motion machine, a clear violation of the sacred laws of thermodynamics. But time crystals don't violate these laws. They cleverly sidestep them by operating in their quantum mechanical ground state, the lowest possible energy configuration a system can have. The idea was first proposed by the Nobel laureate physicist Frank Wilczek in 2012. He was pondering the nature of crystallization. A regular crystal, like a diamond, breaks spatial symmetry. Its atoms are not arranged identically in every direction. They lock into a repeating, periodic pattern in space. Wilczek asked a simple yet profound question: could a crystal also break time symmetry? Could there be a structure whose atoms, even in their ground state, exhibit a pattern that repeats not in space, but in time? Imagine a clock that, once set ticking, continues to tick forever without ever being wound, without any springs or batteries, simply because that is its most natural, lowest energy state. This is the essence of a time crystal, a system that is perpetually in motion, not because it has energy to burn, but because it has nowhere lower to go. It's the quantum equivalent of a perfectly smooth, frictionless ball sitting at the very bottom of a valley, yet still rocking back and forth with a rhythm that never, ever fades. Turning this theoretical speculation into experimental reality was a monumental task that required overcoming significant skepticism. The key was to create a system that was both stable and isolated from its environment, as any external influence would add energy and destroy the delicate, persistent oscillation. Researchers eventually succeeded using two primary methods. One approach involved lining up a string of charged atoms, ions, and hitting them with just the right sequence of laser pulses to nudge them into this exotic state. Another used a dense crystal of impurities within diamond, manipulating the spins of their electrons. In both cases, the result was the same. The system began to oscillate at a period that was different from, and often a multiple of, the driving laser's rhythm. This subharmonic response was the telltale signature. It wasn't just vibrating because it was being pushed. It had found its own innate, protected rhythm and was sticking to it stubbornly. a drum that continues to hum its own tone long after the drummer has left the room. This wasn't perpetual motion, it was perpetual structure in time. The potential implications of this discovery reach far beyond a laboratory curiosity and touch upon the very nature of time in spacetime. In Einstein's relativity, time is woven into the fabric of the universe as a dimension, but it's a dimension that feels fundamentally different from the three of space. We can move freely in space, but we are ruthlessly carried forward in time. The arrow of time, dictated by ever-increasing entropy, only points one way. Time crystals introduce a new, microscopic arrow. They create a preferred direction in time at the quantum level, a regular, repeating beat that could serve as a perfect, immutable quantum clock. This has led to fascinating speculation. Could the fabric of spacetime itself have properties reminiscent of a time crystal on the grandest scales? Is the relentless, rhythmic expansion of the universe, or the steady spin of a pulsar, a faint echo of a more fundamental temporal order? While this remains highly speculative, it forces us to consider that time might not be a featureless backdrop, but could possess its own crystalline structure, a subtle texture that we are only just beginning to perceive. This leads to thrilling possibilities for future technology, particularly in the realm of quantum computing. One of the biggest challenges in building a quantum computer is decoherence, the tendency of fragile quantum states to collapse from the slightest interaction with the outside environment, effectively erasing the information they hold. A time crystal, with its inherently stable, periodic rhythm, could act as a natural safeguard for quantum information. Imagine storing a quantum bit, a qubit, within the unshakable beat of a time crystal. Its constant, predictable oscillation could provide a protected pocket in time, a steady drumbeat that keeps the quantum information synchronized and isolated from disruptive noise. Much like keeping perfect time to a metronome makes it easier to ignore a distracting cacophony. This could be the key to building robust, fault-tolerant quantum memories, bringing us one step closer to unlocking the immense processing power that quantum mechanics promises. And what of cosmology? Could these strange temporal structures have played a role in the universe's infancy? Some theorists have pondered whether phase transitions in the early cosmos, moments when the fundamental forces split from one another, could have frozen time crystals into the very fabric of reality. If so, these temporal fossils might still be oscillating today, their faint rhythm perhaps imprinted on the cosmic microwave background or detectable as a very specific, persistent signal in gravitational wave detectors. The discovery of a cosmological time crystal would be a revelation, proving that the universe's order is not just written in space, but is also etched into the very flow of time, a permanent, rhythmic counterpoint to the general drift toward disorder. It represents a stunning new frontier, showing us that even in a universe governed by entropy, there can exist islands of eternal, unwavering order, dancing to a quantum beat that began at the dawn of creation. Now, we arrive at a concept so profound that it seems to challenge the very core of our experience, the relentless, undeniable flow of time. What if this flow is not a fundamental feature of the universe, but a magnificent illusion, a story we tell ourselves from within a reality that is, in its most complete description, utterly timeless? This is the staggering implication of the Wheeler-DeWitt equation, a daring and controversial attempt to weld quantum mechanics with general relativity that results in a cosmic picture where time, as we know it, simply vanishes from the underlying equations. The quest for a theory of quantum gravity is the single greatest challenge in fundamental physics, an effort to reconcile the probabilistic, granular world of the quantum with the smooth, geometric landscape of spacetime. In the 1960s, the brilliant physicists John Wheeler and Bryce DeWitt took a direct approach. They applied the standard rules of quantum mechanics, the same rules that give us the Schrödinger equation for particles, to the entire universe. They treated the entire cosmic fabric, the geometry of spacetime itself, as a quantum object that must be described by a wave function. The result of this ambitious effort is the Wheeler-DeWitt equation. On its face, it is a monumentally complex formula, but it contains one shocking, simple feature. The variable for time does not appear in it anywhere. It is completely absent. The equation describes the state of the entire universe, but it makes no reference to time passing. It suggests that at the most fundamental level, the universe is static. It just is. To wrap your mind around this, picture the entire history of the cosmos not as a movie, but as a single, frozen sculpture. Imagine a vast, four-dimensional block where the past, present, and future all exist simultaneously and eternally. Your birth, your life, the death of the sun, and the ultimate fate of the universe are all equally real, fixed points within this block. This is the block universe interpretation often associated with Einstein's relativity. But the Wheeler-DeWitt equation takes it a radical step further. It implies that the feeling of time passing, the sensation of the present moment moving forward, is not a feature of the universe itself, but a property that emerges from within it, a perception generated by conscious beings processing information in a certain sequence. In this view, change is the illusion. The true reality is a single, unchanging quantum state of the entire cosmos. John Wheeler himself grappled deeply with this bizarre outcome, famously noting that time is what prevents everything from happening at once, a witty phrase that hints at the problem his own equation created. If time isn't fundamental, what is it that gives us the powerful experience of sequence and duration? This problem of time, as it's known, has spawned a multitude of interpretations, each trying to rescue our everyday experience from a timeless reality. One school of thought, timeless physics, simply accepts the conclusion. Proponents suggest that the flow of time is a cognitive illusion, a necessary artifact of how our brains are wired to perceive a tiny slice of the block universe. Another compelling idea is that time is not gone but hidden. It needs to be found within the system itself. This approach searches for an internal time variable. Think of it like this. If you look at a single, still photograph of a grandfather clock, you cannot tell what time it is. But if you could see the entire clock, the position of its hands, the swing of its pendulum, those elements themselves can be used to define a time relative to the clock's own mechanism. In the same way, perhaps some aspect of the universe's content, like the overall rate of expansion or the motion of matter within it, can serve as a clock against which change can be measured. Time wouldn't be an external parameter on which the universe plays out. It would be a story the universe tells about itself, using its own parts as the characters and the clock. This forces us to confront a question that borders on the philosophical. What is time really? Is it a fundamental river flowing through the universe? Or is it a story we construct from correlation and memory? If the Wheeler-DeWitt equation is correct, then our deepest intuition about reality is a kind of necessary deception. We are like readers who believe a novel is unfolding word by word, when in truth, every chapter, every sentence, already exists completely within the covers of the book. Our consciousness simply moves through it, experiencing each moment in a fixed order, mistaking this journey for a fundamental flow. This doesn't make our experience any less real to us, but it suggests that the ultimate laws of physics might operate in a realm where before and after have no meaning, a realm of pure being that is beyond time. The Wheeler-DeWitt equation doesn't solve the mystery of time. It deepens it to its very core, challenging us to find a place for our fleeting now in a universe that, in its final description, may have no need for it at all. But if the timeless picture painted by the Wheeler-DeWitt equation suggests that change is an illusion, then black holes present us with the ultimate paradox of change itself. What happens to everything that falls in? For decades, these cosmic vacuums were thought to be the universe's ultimate dead ends, the final stop for matter, energy, and information. But in a stunning theoretical breakthrough, we discovered that black holes are not eternal, silent tombs. They have a heartbeat, they have a temperature, they even have a lifespan, slowly fading away over eons due to a subtle, ghostly glow that emerges from the very edge of nothingness. This is the realm of black hole thermodynamics, a breathtaking fusion of gravity, quantum mechanics, and the science of heat that completely reshaped our understanding of these enigmatic objects and gave us our first true glimpse of a deeper, quantum theory of gravity. The story begins in the early 1970s, when a young graduate student named Jacob Bekenstein made a radical proposition that seemed to defy all common sense. He was inspired by a powerful idea from classical thermodynamics, that when you throw something into a black hole, you increase the area of its event horizon. At the same time, you are irretrievably losing something from the observable universe, the entropy, or hidden information, contained within that object. Bekenstein realized that if black holes had no entropy themselves, this would be a fantastic way to violate the second law of thermodynamics. You could simply erase disorder from the universe by tossing it into the hole. His daring solution was to propose that black holes must have entropy, and that this entropy is directly proportional to the surface area of their event horizon. The larger the black hole, the greater its entropy. It was a brilliant insight, but it raised an immediate and profound question. If a black hole has entropy, a measure of disorder and hidden information, then according to the well-established laws of thermodynamics, it must also have a temperature. And any object with a temperature must radiate energy. But how could a black hole, the very definition of an object from which nothing can escape, possibly radiate anything? The idea seemed absurd. Enter Stephen Hawking. Initially skeptical of Bekenstein's idea, he decided to investigate what would happen if you applied the laws of quantum mechanics not to empty space, but to the space just outside a black hole's event horizon. Remember that seething quantum foam, the virtual particles popping in and out of existence everywhere. Hawking realized that this process doesn't stop at the edge of a black hole. It happens there too. Normally, these particle pairs annihilate each other almost instantly. But right at the precipice of the event horizon, a catastrophic divorce can occur. Imagine a virtual particle pair flickering into existence. One particle, through sheer random chance, appears just on the outside of the horizon, while its partner appears just on the inside. The outside particle, now suddenly real and unable to reunite with its trapped partner, can escape, racing away as genuine radiation. The particle that fell inside carries negative energy, which effectively reduces the mass of the black hole. From the perspective of a distant observer, the black hole isn't completely black. It is glowing with a faint thermal radiation, exactly as if it were a warm object. As Hawking himself later recounted, this discovery shocked him. He had set out to prove Bekenstein wrong, and instead, he found the precise mechanism that confirmed his theory. He said, "I was very sorry to disappoint him, but I found that black holes aren't completely black after all." A helpful, though imperfect, analogy is to think of the black hole not as a static pit, but as a warm object sitting in the cold of space, slowly radiating its heat away. A cup of hot coffee left on a table will gradually cool down as it emits infrared radiation. A black hole does the same, but the source of its heat is not molecular motion. It is the relentless, quantum mechanical production of particles at its boundary. This Hawking radiation has a temperature, and that temperature is inversely related to the black hole's mass. A stellar mass black hole has a temperature of barely a fraction of a degree above absolute zero, making its radiation incredibly faint and virtually undetectable against the cosmic microwave background. But a much smaller, hypothetical black hole, say, one the mass of a mountain, would be white-hot, radiating away its energy at a tremendous rate. This radiation is the black hole's death knell. As it radiates, it loses mass. As it loses mass, its temperature increases. As its temperature increases, it radiates even faster. This creates a runaway process that, over unimaginable timelines, causes the black hole to evaporate completely, vanishing in a final, faint burst of particles. The mightiest objects in the universe, it turns out, are ultimately vulnerable to the faintest whispers of the quantum vacuum. This incredible discovery, however, unleashed a paradox that has haunted theoretical physics for 50 years, the black hole information paradox. Quantum mechanics is built on the principle that information is never truly lost. If you burn a book, you could, in principle, collect every single atom and photon from the smoke and ashes, and with a sufficiently powerful computer, reverse the process to reconstruct every word on every page. The information about the book's state is conserved, just scrambled. But what happens when you throw a book into a black hole? According to Hawking's original calculation, the radiation that comes out is purely thermal. It is random noise, completely independent of what fell in. It carries no information about whether it was a book, a star, or a bucket of water that created the black hole. When the black hole finally evaporates and vanishes, all that specific, detailed information seems to have been erased from the universe forever. This violates a fundamental tenet of quantum mechanics, and it suggests a deep incompatibility between our two best theories of reality. As the physicist John Preskill famously bet Stephen Hawking, information must be preserved. Hawking initially believed it was lost, but he later conceded the bet, admitting that he believed the information does in fact escape, though how it does so remains one of the greatest unsolved mysteries in physics. So where does the information go? This is the million-dollar question that pushes us to the absolute frontier of knowledge. Some theories suggest that the information is somehow encoded on the event horizon itself, imprinted there as matter falls in, and then slowly released in a scrambled, encoded form in the Hawking radiation. Others propose more radical solutions, like the existence of a remnant, an incredibly tiny, dense leftover from the evaporation process that contains all the original information locked inside. Or perhaps our very understanding of the event horizon is wrong, and there's a firewall of intense energy there that destroys anything trying to cross, itself a sign of a massive conflict between quantum theory and general relativity. The resolution of this paradox is almost certainly the key that will unlock the door to a full theory of quantum gravity, a set of laws that can describe the center of a black hole where both quantum effects and gravitational curvature are infinite. It forces us to ask not just what black holes are, but what they do. They are not merely destructive engines, they are transformative engines, perhaps converting matter and information into something entirely new, into properties of spacetime itself, into the very curvature and topology of the universe. They are the ultimate laboratories where the laws of physics are stress-tested to their breaking point, revealing that even the void has a memory, and that nothing, not even the deepest darkness, is ever truly final. So if the quantum vacuum is this seething, energetic foam, constantly bubbling with virtual particles, is there any way we can actually reach out and touch it? Can we feel its presence in a way that's more direct than the subtle glow of Hawking radiation? The answer is a resounding yes, and the proof comes from a beautifully elegant experiment that you could almost set up on your kitchen table, if you had plates polished to an almost impossible smoothness and a vacuum chamber to put them in. This is the Casimir effect, and it stands as one of the most stunning and direct pieces of evidence that empty space is not empty at all. It's a literal, measurable force generated by the restless energy of nothingness itself. The effect is named after the Dutch physicist Hendrik Casimir, who, working with Dirk Polder in 1948, made a brilliant prediction. He was thinking about the quantum fluctuations that fill the vacuum and realized they wouldn't be entirely random if you placed constraints on them. Imagine two perfectly smooth, perfectly flat, uncharged metal plates placed incredibly close together in a complete vacuum, just a few nanometers apart, a distance roughly 1,000 times thinner than a human hair. In the vast, open space outside these plates, a limitless number of different quantum fluctuations can occur. The virtual particles can have any wavelength they please. But in the narrow gap between the plates, the rules change. Only certain wavelengths of fluctuations can fit between them. Specifically, only those wavelengths that are whole number fractions of the gap distance. It's like the sound waves between two closely spaced walls. Only certain resonant notes can exist in that confined space. This creates an imbalance. Outside the plates, the full, roaring symphony of the quantum vacuum is playing every possible note. But between the plates, only a limited selection of high-pitched notes is allowed. The result is that there is a greater density of virtual particle activity, and thus a greater quantum pressure, on the outside surfaces of the plates than on the inside surfaces facing each other. This difference in pressure doesn't just sit there. It creates a net, inward force that pushes the two plates together. The nothingness between them is literally less pushy than the nothingness outside. Casimir's calculation showed that this force should be incredibly small, but for very small separations it would be measurable. It would be an attractive force, pulling the plates together, and its strength would depend precisely on the distance between them, varying inversely with the fourth power of that distance. This means that if you have the gap, the force becomes 16 times stronger. A wonderful analogy for this is to picture two large ships resting on a very calm ocean. Normally, the ocean's waves would hit the ships from all sides equally. But if the ships are anchored very close to each other, the situation changes. The long, rolling waves of the open ocean can't easily fit into the narrow channel between the two hulls, but the smaller, choppier waves can. This means the water between the ships is comparatively calmer, with less wave energy and thus less pressure pushing the ships apart, while the full force of the ocean's waves continues to batter their outer hulls. The result is that the two ships will be gently but surely drawn together, nudged by the imbalance in wave pressure. The Casimir effect is the quantum version of this phenomenon, where the virtual particles of the vacuum are the waves, and the metal plates are the ships. The experimental confirmation of this effect, first achieved with good precision in the 1990s by Steve Lamoureux and others, was a landmark moment in physics. It wasn't just a validation of a clever theoretical idea. It was a direct, tactile measurement of the zero-point energy of the vacuum. Researchers placed exquisitely polished plates made of gold or other materials excruciatingly close together in a high vacuum, and they used incredibly sensitive instruments like atomic force microscopes or torsion balances to measure the tiny force between them. The results matched Casimir's predictions almost perfectly. We had reached into the void and felt it push back. We had proven that the quantum foam wasn't just a mathematical abstraction. It was a real physical entity that could move macroscopic objects, a hidden ocean of energy whose waves could be harnessed to do measurable work. This discovery immediately connects back to our earlier discussion about the cosmological constant and the massive discrepancy in vacuum energy. The Casimir effect shows us unequivocally that this energy is real and that it has real gravitational consequences, because all energy curves spacetime. The force measured between those plates is a direct manifestation of the energy density of the vacuum. However, and this is the critical part, the energy density we measure in the Casimir effect is of the same order of magnitude as the theoretical predictions for the local vacuum energy. It's only when we try to add up all the possible quantum fluctuations across the entire universe that we get that catastrophically large number. The Casimir effect works because it's a difference in energy density, not the total sum. This tells us that our quantum field theories are spectacularly accurate for local, laboratory-scale predictions, but they somehow dramatically overcount the global, cosmological vacuum energy. The effect acts as a crucial experimental anchor, a real-world benchmark that any ultimate theory of quantum gravity must be able to explain and reproduce. Beyond confirming a 70-year-old prediction, the Casimir effect has become a vital tool for testing the very frontiers of physics. It is used to probe the limits of the standard model and to search for new forces. Some theories predict the existence of new, very light, very weakly interacting particles. These particles could mediate a new type of force that would create a slight deviation from the predicted Casimir force at certain distances. By repeatedly conducting these exquisitely precise experiments, physicists are essentially using the vacuum itself as a detector, looking for any anomalous attraction or repulsion between plates that could signal new physics lurking just beyond our current understanding. It's a way of listening for faint, new notes in the symphony of the vacuum. This inevitably sparks the imagination and leads to a tantalizing, though currently speculative, question. If we can already measure this force, could we ever learn to control it? Could we one day harness the energy of the vacuum for propulsion or power? The idea of extracting limitless energy from empty space has long been a staple of science fiction, but the reality, as it stands, is fraught with immense difficulty. The Casimir effect doesn't give us a reservoir of energy to tap. It demonstrates a force that arises from a difference in energy density. To do continuous work with it, you would need to find a way to create a perpetual imbalance, perhaps by constantly moving the plates or by finding a material that could somehow shield or amplify specific quantum fluctuations. Most physicists consider the possibility of practical vacuum energy extraction to be extremely remote, as it would seem to violate fundamental thermodynamic principles. However, the effect is already being seriously studied in the realm of micro-electromechanical systems, or MEMS, where tiny, moving parts operate at these microscopic scales. Here, the Casimir force isn't a source of power but a potential nuisance, a quantum stickiness that can cause nanoscale gears and actuators to unexpectedly weld themselves together. Understanding and mitigating this effect is crucial for the future of nanotechnology, proving once again that even the most abstract quantum phenomena have a way of reaching up and influencing our world in the most practical of ways. We've seen how mass creates gravity's curves and how energy and pressure add their own unique warps to the cosmic fabric. But what happens when that mass isn't just sitting still? What if it's spinning? This brings us to a remarkably subtle yet profound phenomenon where the universe itself gets caught in a cosmic whirlpool, an effect that turns the static image of spacetime into a dynamic, swirling vortex. This is frame dragging, a prediction of Einstein's general relativity where a rotating massive object doesn't just bend the spacetime around it. It actively twists it, pulling the very fabric of reality around in a slow, relentless drag, as if space itself were a viscous fluid being stirred by a giant, invisible spoon. The best way to picture this is to imagine a large, heavy sphere submerged in a very thick liquid like honey. If the sphere is perfectly still, it will create a simple, stationary depression in the honey. But now, set that sphere spinning. As it rotates, its rough surface grips the surrounding honey, pulling it around in a circular motion. The honey closest to the sphere moves the fastest, caught in its grip, while the currents weaken with distance. The entire fluid around the sphere begins to circulate, creating a swirling vortex that extends outward from the surface. This is precisely what a rotating planet or star does to spacetime. It's not enough to simply curve the stage. A spinning mass actually grabs the curtains of the universe and pulls them along for the ride. The moon's orbit around the Earth, for instance, isn't just a simple ellipse dictated by our planet's mass. It's also minutely influenced by the fact that the Earth is constantly turning, ever so slightly dragging the local spacetime around with it. For decades, this effect remained a tantalizing but unproven prediction, a subtlety hidden within Einstein's complex equations. The great man himself acknowledged the intricate and strange nature of rotational gravity, understanding that a spinning mass would generate a gravitational field far more complex than that of a stationary one. Detecting this incredibly faint influence, however, was a monumental technological challenge. It required an experiment of almost unbelievable precision, one that could measure an angle so small it was the equivalent of measuring the thickness of a sheet of paper from 100 miles away. This challenge was finally met by the Gravity Probe B mission, a NASA project decades in the making. The spacecraft was essentially an orbiting gyroscope, one of the most perfect spheres ever created, spinning in a near-perfect vacuum while pointed at a distant guide star. According to Newtonian physics, the spin axis of these gyroscopes should have remained fixed in space forever. But according to Einstein, the gentle, swirling drag of Earth's rotation would ever so slowly tilt the gyroscope's orientation over time. After a year of painstaking data collection and analysis, the results were clear. The gyroscopes had drifted. The universe, it was confirmed, does indeed get dragged. The implications of frame dragging extend far beyond our planet's immediate vicinity, becoming spectacularly dramatic near the most extreme rotating objects in the cosmos, spinning black holes or Kerr black holes. The spacetime around these objects isn't just slightly stirred. It's whipped into a frenzied, tornado-like maelstrom. Close to a rapidly spinning black hole, the frame dragging becomes so powerful that it's impossible to stand still. Imagine you're an astronaut trying to hold a position near the event horizon. Even if you fire your thrusters at full power against the direction of the spin, you would find yourself helplessly swept along by the current of twisting spacetime, like a kayaker trying to paddle against a Class 5 rapid. There is a region outside the event horizon, called the ergosphere, where the dragging of spacetime is so intense that not even light can move in the opposite direction to the black hole's rotation. Everything within this region is forced to co-rotate with the black hole, a testament to the raw, dynamical power of a spinning singularity. This relentless twisting of spacetime also warps the flow of time itself in fascinating ways. We've already discussed gravitational time dilation, where time slows down in a strong gravitational field. Near a rotating black hole, you get an additional effect. Your clock's speed depends on which direction you're moving. If you orbit in the same direction as the black hole's spin, you're moving with the current of dragged spacetime, and time for you will pass more slowly relative to a distant observer than if you were orbiting in the opposite direction, fighting against the current. This directional dependence of time is a unique signature of rotational gravity, a subtlety that adds yet another layer of complexity to Einstein's vision of a flexible, relative universe. Contemplating the navigation near such an object is an exercise in cosmic wonder. How would you plan a trajectory into the ergosphere of a spinning black hole, where the very coordinates of space and time are being swept along in a torrent? Could we ever harness this incredible rotational energy? Theorists like Roger Penrose have shown that it's actually possible to extract energy from a rotating black hole by dropping an object into the ergosphere and splitting it in two, with one piece falling in against the rotation and the other escaping with more energy than it started with. This Penrose process is a direct exploitation of the black hole's rotational energy, a way of borrowing from the immense spin of spacetime itself. Frame dragging transforms black holes from simple vacuum cleaners into powerful, spinning engines, capable of energizing particle jets that scream across galaxies and fundamentally shaping the environment around them, proving that rotation is not just a detail but a central actor in the grand mechanics of the cosmos. But if the relentless spin of a massive object can drag the fabric of spacetime around it, what happens when we consider not just motion through space, but the very nature of motion itself? This brings us to one of the most mind-bending demonstrations that reality is not absolute, but deeply personal, shaped by our own state of being. It's called the Unruh effect, and it reveals that the seemingly empty vacuum of space is not the same for everyone. What looks like a serene, particle-free void to one observer can appear as a swirling, hot soup of radiation to another, depending entirely on how they are moving. This phenomenon shatters the classical notion of a single, objective reality, and shows us that acceleration itself can conjure particles from the nothingness, weaving a direct and profound connection between motion, heat, and the quantum nature of spacetime. To understand this, we need to revisit our quantum vacuum, that seething sea of virtual particles. We know these fleeting fluctuations are everywhere. Now, imagine an observer floating freely in the depths of space, completely weightless and non-accelerating. For this observer, the vacuum appears just as we expect, empty, quiet, and cold. But now, imagine a second observer who fires up a rocket engine and begins to accelerate through this same patch of space at a constant, relentless rate. According to the work of physicist Bill Unruh, who first described this effect in 1976, this accelerating observer would have a completely different experience. Their rocket-powered journey would not be through a silent void. Instead, they would find themselves flying through a warm bath of real, detectable particles. From their perspective, the empty space has heated up, and they are surrounded by a thermal glow of radiation, a phenomenon that is completely undetectable to their stationary friend. A powerful, though imperfect, analogy is the experience of wind on a perfectly still day. If you are standing motionless, the air around you feels calm and placid. But if you begin to sprint, you suddenly feel a rush of wind against your face. The wind isn't suddenly appearing in the world. Your state of motion is creating the sensation of it. The Unruh effect is the quantum field theory version of this. The accelerating observer isn't creating particles out of nothing in an absolute sense. Rather, their own accelerated motion through the quantum field prevents them from seeing the same vacuum state as the inertial observer. Their different path through spacetime means they interact with the quantum fields in a different way. And that interaction is exactly what they interpret as being surrounded by a swarm of real particles. It's a profound demonstration that the concept of a particle is not an invariant building block of the universe, but a relative one, dependent on the observer's own journey. The temperature of this phantom heat bath is directly tied to the acceleration. The harder you press on the gas pedal, the hotter the surrounding radiation becomes. However, the effect is incredibly weak for any acceleration we can realistically achieve. To experience an Unruh radiation bath as warm as room temperature, you would need to accelerate at a rate of a quintillion times the force of gravity here on Earth, a rate that would pulverize any known material and is far beyond our current technology. This is why we don't notice it in our everyday lives, but for theoretical physics, its implications are earth-shattering. Bill Unruh himself has often used vivid language to explain the counterintuitive nature of his discovery, emphasizing that it forces us to abandon the idea of a single, God's-eye view of the universe. He has said, "The vacuum is not a vacuum," meaning its appearance is entirely in the eye of the beholder, or more precisely, in the accelerometer of the beholder. This discovery creates a beautiful and deep partnership with Hawking radiation. Hawking showed that a stationary observer far from a black hole sees radiation coming from it, while an observer falling in freely would see none at the horizon. The Unruh effect provides the other side of the same coin. An observer constantly accelerating in flat space sees radiation, while an inertial observer sees none. This deep connection suggests that gravity and acceleration are not just similar through the equivalence principle. They are fundamentally linked in how they affect quantum fields. The event horizon of a black hole acts as a point of no return for trajectories, creating a barrier that effectively splits the perspectives of different observers, much like constant acceleration does in empty space. This hints at a universal truth. Horizons of all kinds, whether caused by gravity or motion, have a temperature and radiate. This forces us to confront a deeply unsettling question about the nature of reality. What is the true, fundamental state of the quantum field? Is there such a thing? The Unruh effect suggests there isn't a single answer. The vacuum is a fluid, malleable concept. Your reality is quite literally determined by your path through the cosmos. This has profound implications for the equivalence principle, the cornerstone of general relativity, which states that the effects of gravity are locally indistinguishable from the effects of acceleration. The Unruh effect strengthens this by showing that both situations, standing on a massive planet or accelerating in a rocket, can generate thermal phenomena from the quantum vacuum. It suggests that the warmth you feel on your skin standing in the sunlight and the warmth an astronaut would feel from Unruh radiation during extreme acceleration are, at their heart, manifestations of the same underlying quantum mechanical principle. Ultimately, the Unruh effect teaches us that the universe is not a static stage with a fixed set of props. It is a dynamic, interactive medium where observation and participation are inextricably linked. The very act of moving through spacetime in a particular way changes what you see and experience, conjuring particles and energy from the dance between your own trajectory and the invisible quantum fields that fill the void. It ties the most fundamental quantum properties of matter directly to the geometry of motion, proving that the engines of the cosmos are not just out there in the distant stars, but are intimately connected to our own state of being, reminding us that we are not just observers of the universe, but active participants in its endless creation. Yet if our journey through these invisible engines has taught us anything, it is that the universe is far stranger and more imaginative than we could ever conceive on our own. This realization pushes us toward the most expansive and speculative idea of all, the concept of the multiverse. What if our entire cosmos, with its elegantly tuned constants and its specific flavor of spacetime, is not the whole of reality, but merely one single bubble in a vast, frothing cosmic ocean? One universe among an infinite number of others, each with its own unique physical laws, its own dimensions, and its own story. This is not mere science fiction. It is a serious, though highly theoretical, extension of our most successful physical theories, a framework that attempts to place our local reality within a context of literally unimaginable plurality. This staggering idea emerges naturally from two of the most powerful theories we've already explored: eternal inflation and string theory. Imagine the inflationary field that blew our universe up from a quantum speck. The theory suggests that this inflation might not be a one-time event that started and stopped everywhere. Instead, it could be a perpetual process, a meta-reality that is endlessly inflating. In this eternally expanding background, quantum fluctuations would continuously cause tiny pockets of that inflating space to suddenly drop into a lower energy state, much like random bubbles forming in a pot of boiling water. Each one of these bubbles would stop inflating internally and would instead begin its own independent evolution, cooling down to form its own distinct universe with its own particles and forces. Our entire observable universe, from the Big Bang to the present day, would be just one such bubble in an infinite, ever-growing foam of other universes. This is the inflationary multiverse. String theory adds another, even more diverse layer to this picture. This theory, which posits that the fundamental building blocks of reality are tiny, vibrating strings, requires extra dimensions of space to work mathematically. But the theory allows for a colossal number of different ways for those extra dimensions to be curled up and compactified, perhaps 10 to the 500 different ways. Each distinct configuration would result in a universe with completely different physical laws, different constants, and different fundamental particles. This creates a vast landscape of possible universes, And the inflationary bubble multiverse could be randomly creating real, physical universes that realize every single one of these possibilities. In this view, the specific laws of physics we observe are not deeply fundamental. They are more like local bylaws, the accidental outcome of how our particular bubble formed and cooled. A helpful, though vastly simplified, metaphor is to picture a boundless, stormy ocean. On the surface, countless bubbles are constantly forming, rising, and popping. Each bubble is a self-contained pocket of air, isolated from the others. Our universe is one such bubble. We can only perceive the interior of our own bubble. We cannot see or touch the others, or even the ocean itself. The laws of physics, inside our bubble, like the strength of gravity or the mass of the electron, are simply the properties of our particular pocket of air. Another bubble might have entirely different properties, a different atmosphere altogether. Some bubbles might be stable and long-lasting, like ours. Others might pop into existence and immediately collapse, or be filled with forces so violent that no structures can ever form. The physicist Max Tegmark has provided a useful framework for this, classifying different levels of multiverse, from the simple idea of regions beyond our cosmological horizon to the more radical mathematical universe hypothesis, which suggests that every mathematically consistent structure actually exists as a physical reality somewhere. This framework offers a dramatic and compelling solution to the mystery of fine-tuning that we encountered with the cosmological constant and other physical parameters. The values of these constants appear perfectly calibrated for the existence of life. If gravity were slightly stronger, stars would burn out too quickly. If the weak nuclear force were slightly weaker, hydrogen wouldn't fuse into the heavier elements essential for planets and life. The traditional question has been, why is the universe so perfectly tuned for us? The multiverse concept provides a powerful answer. It isn't. In an infinite multiverse, every possible value for every constant is realized in some universe. The vast, overwhelming majority of these universes are sterile and lifeless places where atoms never form, or where black holes dominate instantly, or where the fabric of spacetime is too unstable for anything to exist. We, of course, can only find ourselves in one of the exceedingly rare universes where the constants are just right for creatures like us to evolve and ask these very questions. There is no designer, there is only a monumental selection effect. We are the lucky winners of a cosmic lottery whose odds are beyond comprehension. This inevitably leads to the most pressing and difficult question of all. Could we ever find evidence for other universes? If they are truly separate, causally disconnected bubbles, then by definition, no signal from another universe can ever reach us. They exist beyond our cosmological horizon, forever outside the realm of direct observation. However, scientists are a creative bunch, and they have proposed some tantalizing, if highly speculative, possibilities. One idea is that if our universe collided with another bubble universe in the distant past, the immense energy of that collision could have left a permanent, anisotropic imprint on the cosmic microwave background, a kind of cosmic bruise on the sky. Astronomers have actively searched for such patterns, though no conclusive evidence has been found. Another possibility involves the detection of exotic particles or forces that could only have seeped into our universe from a neighboring brane in a higher dimensional bulk, a concept from string theory. While these ideas push the limits of experimental science, they demonstrate that the multiverse is not strictly a metaphysical idea. It is a physical theory that can, in principle, make testable predictions, however faint they might be. Contemplating the multiverse is ultimately a humbling and perspective-shifting exercise. It suggests that all the intricate mechanics we've explored, the curvature from mass, the push of dark energy, the turbulence of the quantum vacuum, might be nothing more than the local customs of our particular cosmic neighborhood. In the universe next door, Gravity might be a billion times stronger, or time might have two arrows, or the very concept of spacetime as a four-dimensional continuum might not exist at all. This idea does not diminish our universe. It makes the fact that we are here to understand any of it at all seem like the most spectacular and precious accident. It places our entire reality within a context of infinite variation, suggesting that the true nature of existence is far grander, more complex, and more wonderfully bizarre than we could ever have dreamed. But if the universe is a frothing multiverse of infinite possibilities, and if even the vacuum is alive with energy, we are forced to ask the most fundamental question of all: what is the stage itself made of? We've explored how mass, energy, and motion shape spacetime, but what if spacetime isn't the foundation? What if the cosmic fabric, with its three dimensions of space and one of time, isn't the starting point of reality, but the grand finale? This is the radical proposition of emergent spacetime, the idea that the universe we perceive is not built from a continuous, smooth fabric, but is instead a magnificent illusion that arises from something far stranger and more fundamental: a vast, buzzing network of quantum information, where the very concepts of here and there are born from connection rather than containment. To grasp this, let's step away from the cosmos and consider a much more familiar illusion: a digital photograph on your screen. When you look at it from a normal distance, you see a smooth, continuous image, a face, a landscape, a beautiful gradient of color and light. But if you zoom in incredibly close, that illusion of continuity shatters. The image resolves into a grid of tiny, discrete blocks of color, pixels. Each pixel has a single, specific color value. It is either on or off, red or blue. There are no half measures at the fundamental level. The beautiful, smooth image you see is not primary. It is an emergent property, a large-scale consequence of the collective behavior of countless tiny, individual bits of information. The theory of emergent spacetime suggests that our reality works in a very similar way. The smooth, curved geometry of general relativity, the stage on which planets and stars perform, may not be fundamental. It might be the high-resolution picture that emerges from a universe-sized grid of unimaginably tiny pixels of information, operating at the Planck scale. This stunning idea finds its most concrete expression in a profound mathematical discovery known as the AD-S/CFT correspondence, pioneered by physicist Juan Maldacena. This is not just a theory. It's a kind of cosmic dictionary that translates between two completely different languages describing reality. On one side of this correspondence, you have a theory of gravity playing out in a hypothetical, warped higher dimensional volume of space. On the other side, you have a conformal field theory, a quantum theory without any gravity at all, that lives on the lower dimensional boundary of that volume. The miracle is that these two descriptions are mathematically exactly equivalent. They are two different ways of talking about the exact same thing. As Maldacena's work showed, a theory of quantum particles interacting on a flat, lower dimensional surface can perfectly describe a theory of gravity and curved spacetime in a higher dimensional bulk. It strongly implies that the gravity we experience in our three-dimensional world might be a holographic projection, a shadow cast by complex quantum interactions happening on a distant, two-dimensional surface. The geometry of spacetime in this view is not the starting point. It is the output, the consequence of a deeper, non-geometric computation. This perspective offers a breathtakingly elegant path to resolving the central conflict in modern physics, the problem of quantum gravity. For a century, we have struggled to force the smooth, deterministic geometry of general relativity to coexist with the fuzzy, probabilistic rules of quantum mechanics. The equations break down at the center of black holes and the beginning of the Big Bang. But if spacetime itself is not fundamental, then this entire conflict might be a misunderstanding. It would be like trying to explain the phenomenon of wetness by studying individual water molecules. A single H2O molecule isn't wet. Wetness is a collective, emergent property that only appears when you have a vast ensemble of molecules interacting. In the same way, the singularities that break our equations might be artifacts of trying to apply a smooth, continuous description to a reality that is, at its heart, discrete and informational. A theory of quantum gravity wouldn't be about quantizing spacetime. It would be about showing how spacetime itself condenses out of an underlying quantum system, much like a wave emerges from the collective motion of water molecules, yet is not any single one of them. This forces a deeply philosophical shift in how we view existence. For all of human history, we have taken space and time as the given, the immutable stage. Matter and energy were the actors that moved upon it. But emergent spacetime turns this picture completely upside down. It suggests that the true fundamental ingredients of the cosmos are not things located in space, but rather relationships, specifically quantum entanglement. Imagine a vast, cosmic web where every fundamental quantum bit is entangled with countless others in a complex, non-local network. The geometry of spacetime, with its distances and its curvature, might simply be a way of encoding the strength of these entanglement connections. Two bits that are highly entangled might be described as being close together in the emergent spatial geometry, while weakly entangled bits are far apart. In this view, space isn't the container for the network. The network is the reality, and space is just a useful, approximate way to visualize its connectivity. We are not physical objects moving through a void. We are patterns of information in a cosmic computation, and the stage we perform on is itself part of the show. We have traveled an incredible path together, from the deep, mass-warped wells of gravity to the mysterious, repulsive push of dark energy, from the ghostly dance of quantum fluctuations to the radical idea that spacetime itself might be a grand illusion emerging from a deeper reality. Each of these invisible engines reveals another intricate layer of the cosmic machinery, showing us a universe that is infinitely more dynamic, more interconnected, and more wonderfully bizarre than a simple, static stage. This journey does more than just explain why planets orbit and galaxies spin. It fundamentally challenges our most basic assumptions about the nature of reality, time, and our own place in this vast expanse. We are not merely passive observers on a fixed platform. We are active participants in a living, breathing cosmos where the very fabric of existence is constantly being woven and rewoven by these hidden forces. The true wonder is that this is not the end of the story but merely the latest chapter in a grand, ongoing exploration. Every mystery we solve seems to reveal two new questions, each more profound than the last. The enigma of dark matter and dark energy, the search for a theory of quantum gravity, the puzzle of why the universe is so perfectly tuned for life. These are not roadblocks but invitations, calling us to look deeper and think bigger. With every new telescope that peers farther back in time, every more sensitive detector that listens for the faintest ripple in spacetime, and every bold theoretical leap that reimagines the foundations of physics, we are drawing back the curtain a little further on the magnificent spectacle of the cosmos. We are getting closer, piece by piece, to understanding the grand tapestry into which all of these threads, gravity, quantum fields, entropy, and information, are ultimately woven. Thank you so much for embarking on this intellectual adventure. If this journey through the invisible engines that shape our reality sparked your curiosity, please consider liking this video and subscribing to the channel for more deep dives into the wonders of the universe. I am incredibly eager to hear which part of this exploration resonated most with you. Was it the sheer weirdness of quantum entanglement, the terrifying grandeur of black holes, or the humbling scale of the multiverse? Share your thoughts and your own questions in the comments below. The conversation is one of the best parts of this journey, Until our next exploration into the mysteries of existence, keep looking up, keep wondering, and never stop asking what other invisible engines are out there. Quietly power the